Hello everyone, let's go over review sheet number 3. First problem, part A. Show that the set of real number has less cardinality than the set of real number square. So to show a set has less cardinality, we try to show that there's a one-to-one from one set to the other set. So let's try to find a one-to-one function from R to R square. So let f from R to R square. R square means a pair of real number. R means a real number. R square means an ordered pair of real numbers. Let f from R to R square be defined as f of x equal to x comma 0. Then we try to show this is a one-to-one function. Let S1, S2 belong to the domain. Let S1, S2 belong to the domain. Assume f of S1 equal to f of S2. We try to prove S1 equal to S2. We try to prove S1 equal to S2. F of S1 equal to f of S2. That means if I plug in S1 to the function, I have S1 comma 0 equal to S2 comma 0. And this is ordered pair. If they are the same, each component must be the same. 0 equal to 0. So S1 equal to S2. Since f of S1 equal to f of S2 implies S1 equal to S2, that means f is one-to-one. If there's a one-to-one from R to R square, then the set of real number has less cardinality than the set of real number square. Part B. Let U be the set of x belong to 0, 1, where x is rational. Let V be the set of x belong to the interval of 0, 1, where x is irrational. Show that set U has less cardinality than set V. So here, part B, we try to show set U has less cardinality than set V. Since U is a subset of rational number, since U is a subset of rational number, here U is a subset of real number, every number in U is a rational number. So U is a subset of rational number. And we know that rational number, the set of rational number is countable. Since U is a subset of rational number, and the set of rational number is countable, then set U must be countable. Then U is countable because every subset of a countable set is countable. Since U is a subset of rational number and rational number is countable, then U must be countable since every subset of countable set is countable. Next, we try to prove that V is uncountable. Next, we try to prove that V is uncountable. If V is countable, assume V is countable. We try to show V is uncountable. Assume V is countable. Then U union V. Then the union of two countable sets is countable. Then the union of two countable sets is countable. Then the union of two countable sets is countable. But U union V is the interval from 0 to 1. U union V is the interval from 0 to 1 because U represents all rational number between 0 and 1. V represents all irrational number between 0 and 1. If I combine U, V together, I get an interval from 0 to 1. This interval from 0 to 1 is uncountable. But this interval from 0 to 1 is uncountable. So U and V cannot be countable. So U union V is uncountable. Therefore, V must be uncountable. Therefore, V must be uncountable. If V is countable, 0 and 1 will be countable. That's impossible. Since the interval from 0 to 1 is uncountable, V must be uncountable. Therefore, V must be uncountable. Since U is countable, V is uncountable, then since U is countable, and V is uncountable, then the cardinality of U is strictly less than cardinality of V. Cardinality of a countable set is strictly less than cardinality of an uncountable set. That's part B. Part C. Let S be the set of even integers. Show that S is countable. Part C. Let S be the set of even integers. Show that S is countable. Part C. Since the set of integer is countable, since S is a subset of integers, even number is a subset of integers, and the set of integer is countable, since S is a subset of integers and the set of integer is countable, then S is countable. Every subset of a countable set is countable. Since S is a subset of integer is countable set. Every subset of a countable set is countable, so S is countable. Part D. Let A be the set of integers which congruent to 3 mod 4. Let B be the set of integers which congruent to 5 mod 6. We try to show that set A and B have the same cardinality. To show two sets have the same cardinality, we must show that there's a bijection between two sets. To show that two sets have the same cardinality, we must show that there's a bijection between two sets. So let's try to list set A and set B. If possible, let's try to list set A and part B, set A and set B, and try to find a bijection between two sets. If I list set A out, A is a set of integer that congruent to 3 mod 4. So 3 in the middle, 3 plus 4 is 7, 7 plus 4 is 11, 11 plus 4 is 15, and so on. On the other side, 3 minus 4 is negative 1, negative 1 minus 4 is negative 5, negative 5 minus 4 is negative 9. That's set A. If I try to list set B, we have number 5 in the middle, 5 plus 6 is 11, 11 plus 6 is 17, 17 plus 6 is 23. On the other side, 5 minus 6 is negative 1. Negative 1 minus 6 is negative 7. Negative 7 minus 6 is negative 13. That's set A and set B. We try to find a bijection between two sets. That means we try to find a function that map 3 to 5, 7 to 11, map 11 to 7, 15 to 23. So we try to find a function that map we try to find a function that map 3 to 5. It maps 7 to 11. (11 to 17). We try to find a function map 3 to 5, 7 to 11, 11 to 17. It looks like it's a straight line. It looks like the graph is a straight line here. So for this straight line, equation of a straight line is y equal to ms plus b. Equation of straight lines, y equal ms plus b. Slope is y2 minus y1 over x2 minus s1. If I use these 2 points, 3, 5 and 7, 11, y2 minus y1 is 11 minus 5 over x2 minus s1 over 7 minus 3, that's 6 over 4, which is 3 over 2. Once I know the slope, I can use slope to find y-intercept. Use one of the point to find the y-intercept. Let me use the first point. Phi equal to 3 over 2 times x plus b. Phi equal to 9 over 2 plus b. So b equal to a half. So this line can be rewritten as y equal to 3 over 2x plus 1 over 2. Let's try this function. So let function f from a to b be defined as f of x equal to 3 over 2x plus a half. We need to show that this function f is a one-to-one and onto. We need to show that this function f is a one-to-one and onto. One-to-one, it means for all s1, s2 in a domain, assume f is a function from a to b. One-to-one means for all s1, s2 in a domain, if f of s1 equal to f of s2, then s1 equal to s2. That's how we show function is one-to-one. So assume that s1, s2 belong to set A. Assume f of s1 equal to f of s2. Then I substitute s1, s2 here. I have 3 over 2 s1 plus half equal to 3 over 2 x2 plus a half. If I subtract half from both sides, then 3 over 2 s1 equal to 3 over 2 s2. If I divide both sides by 3 over 2, I have s1 equal to s2. If I divide both sides by 3 over 2, I have s1 equal to s2. So f is one-to-one. Next, I try to show f is onto. Onto says for all y, onto means for all y in B, there's x in A, such that f of x equal to y. For all y in B, there's x in A, such that f of x equal to y. So for onto, let y belong to B. Let y belong to set B. We try to find x in A. We try to find x in A, such that f of x equal to y. Let y belong to B. B is the set. X is integer. X congruent to 5 plus 6. Since y belong to B, then y congruent to 5 plus 6. Since y belong to B, y must satisfy the condition in set B. So y congruent to phi must 6. Then y congruent to phi must 6. Y congruent to phi must 6 means y equal to phi plus 6t, where t is an integer. Y congruent to phi must 6 means y equal to phi plus 6t, where t is an integer. I try to find x. I try to find x in A. I try to find x in A such that f of x equal to y. So I can solve this equation. Solve this equation for x. Y equal to 3 over 2x plus a half. If I solve this equation for x, I can first of all multiply both sides by 2. 2y equal to 3x plus 1. Subtract 1 from both sides. 2y minus 1 equal to 3x. So s equal to 2 over 3y minus 1 over 3. So x equal to 2 over 3y minus 1 over 3. Does this x belong to set A? We need to find x in set A. Does this x belong to set A? Let's check. S equal to 2 over 3y is 5 plus 6t. If I plug in 5 plus 6t minus 1/3, what do we get? S equal to 10 over 3 plus 4t minus 1 over 3. 10 over 3 minus 1 over 3 is 9 over 3. 9 over 3 is 3. S equal to 3 plus 4t. S equal to 3 plus 4t. If S equal to 3 plus 4t, then if S equal to 3 plus 4t, then x congruent to 3 must 4. Then x congruent to 3 must 4. Since x satisfies the condition of set A, then I can say x belongs to set A. So x belongs to set A, and f of x is f of 2 over 3y minus 1/3. If I substitute this into function f, 2 over 3y minus 1/3. If I substitute into function f, I have 3 over 2 times 2 over 3y minus 1/3 plus a half. I plug in 2 over 3y minus 1/3 for x. Then if I simplify, I have y minus a half plus a half, distribute 2/3. Y minus a half plus a half, which is equal to y. So for all y in B, there's an x in A, such that f of x equal to y. So f is on 2. Hence, since f is 1-to-1, f is on 2, hence I can say f is a bijection. Hence f is a bijection. Since there's a bijection from A to between set A and set B, then we say A and B has the same cardinality. So set A and set B have the same cardinality. Part E. Let A and B be real numbers with A less than 0, B greater than 0. Show that the interval from A to 0 and the interval from 0 to B have the same cardinality. In order to show two sets have the same cardinality, we must show that there's a bijection between two sets. Let's try to find a bijection between these two intervals. interval from a to 0, somewhere here. That's interval from a to 0. Interval from 0 to b, somewhere here. That's interval from 0 to b. We try to find a function that map every point in this set to every point in this set. So I try to find a function that map a to b and let map 0 to 0. We try to find a function that map a to b, 0 to 0. It looks like we can use a straight line to be the function. It looks like we can use this straight line here to be the function. This function goes through 2 points, a comma b and 0 comma 0. This function goes through 2 points, a comma b and 0 comma 0. So this is a straight line. Equation of straight line can be represented as y equal to ms plus b. Slope is y2 minus y1 over x2 minus s1. b minus 0 over a minus 0, which is b over a. That's the slope of this line. Y-intercept is 0. For this line, the y-intercept is 0. So this equation of line can be rewritten as y equal to b over ax. Y equal to b over ax. That's the equation of this line. So let function f from the interval a comma 0 to 0 comma b be defined as f of x equal to b over a times x. F of x equal to b over a times x. We need to show that this function is 1 to 1 and onto. So to show this function is 1 to 1, let S1, S2 belong to the domain. Let S1, S2 belong to the domain. Assume f of S1 equal to f of S2. Assume f of S1 equal to f of S2. Then we have b over a S1 equal to b over a S2. If I divide both sides by b over a, if I divide both sides by b over a, S1 equal to S2. If I divide both sides by b over a, then S1 equal to S2. So f is 1 to 1. Since both a, b are not 0, I can divide both sides by non-zero integers. If I divide both sides by non-zero integers, the left side and right side still equal to each other. If I divide both sides by non-zero integers, if I divide both sides by non-zero numbers, in the equation left side still equal to the right side. So f is 1 to 1. Next, we try to show f is onto. Next, we try to show f is onto. We try to show that for all y in the codomain, there's x in the domain such that f of x equal to y. So let y belong to the interval 0 comma b. Let y belong to 0 comma b. Then y is between 0 and b. Then y is between 0 and b. We try to find x in the domain. Such that f of x equal to y. So if I solve this equation for x, y equal to b over ax. If I solve this equation for x, x can be rewritten as a over by. X can be rewritten as a over by. Since which next we try to show that x belongs to the domain. Next, we try to show that this x belongs to the domain. Since y is between 0 and b, if I multiply both sides by a, by letter a, the inequality will be switched. inequality sign will be switched because a is less than 0. If I multiply this inequality by a, the inequality sign will be switched because a is less than 0. Because a is less than 0. Then this inequality can be rewritten as AB. This inequality can be rewritten as AB less than AY less than 0. If I divide both sides by b, since b is positive, if I divide both sides by b, inequality sign stays the same. So I have a is less than a over by less than 0. If I divide both sides, if I divide each term by b, the inequality sign stays the same because b is positive. And we know a over by is x. So x is between a and b. X is between a and 0. X belongs to the interval from a to 0. So let y belong to the interval from 0 to b. Let y belong to the codomain. There's x in the domain. There's x in the domain such that f of x is f of a over by because x is a over by. If I substitute a over by into function f, here, I have b over a times a over by. A over b and b over a get cancelled, we get y. So for all y in the codomain, there's x in the domain such that f of x equal to y. So f is onto. For all y in the codomain, there's x in the domain such that f of x equal to y. So f is onto. Since f is 1-to-1 and onto, then f is a bijection. Hence, f is a bijection. Hence, f is a bijection. So, if there's a bijection between two intervals, if there's a bijection between two sets, these two sets have the same cardinality. So the cardinality of the first interval, a, 0, is the same as cardinality of the second interval, 0, b. To show two sets have the same cardinality, we must show that there's a bijection between two sets. Part F. Let S be the set of all bit strings. Show that S is uncountable. To show S is uncountable directly is very hard. Let's do this. Let U be the set of all infinite bit strings. Let U be the set of all infinite bit strings. Then U is a subset of S. S is the set of all bit strings. U is the set of all infinite bit strings. So U is a subset of S. Every element in U belongs to S. U is a subset of S. If we can show that U is uncountable, then S must be uncountable. If we can show that S has an uncountable subset, then S is uncountable. If we can show that U is uncountable, then we can show S is uncountable. So we try to prove U is uncountable by contradiction. We try to prove U is uncountable by contradiction. Assume U is countable. Assume U is countable. Then there's a bijection from natural number to U. Then there's a bijection between the set of natural number and U. Then there exists a bijection F from natural number to u. If u is countable, there exists a bijection from the set of natural number to u. Assume f of 1 equal to a string, say s1. S1 is a string that contains digits D11, D12, D13, and so on. F of 2 equal to S sub 2. F of 2 equal to S sub 2. They equal to D21, D22, D23, D24, and so on. F of 3 equal to S sub 3. They equal to D31, D32, D33, D34, and so on. We try to show that this function f is not on 2. We try to show that this function f is not on 2. We try to show that this function f is not on 2. That means we try to find an element in the codomain in U, such that doesn't belong to the range of f. So assume f of 1 is s1, f of 2 is s2, f of 3 is s3. Then we know that the range of f is the set of s1, s2, s3, and so on. We try to show that f is not on 2. That means we try to find an element in the codomain that doesn't belong to this S. We try to find an element in the codomain that doesn't belong to the S. Let u, lowercase u, let u be a string, let u be an infinite string. Let an infinite bit string u be defined as. Let an infinite bit string u be defined as u equal to D1, D2, D3 are digits. U equal to D1, D2, D3, D4, and so on. Where digits di equal to 0 if dii equal to 1, equal to 1 if dii equal to 2. Let di equal to 0 if dii equal to 1. Let di equal to let di equal to 1 if di equal to 0. So for example, if d11 it could be either 0 or 1. If d11 is 0, I let d1 equal to 1. If d11 is 1, I let d1 equal to 0. So di doesn't equal to dii for all I. So d1 doesn't equal to d11. D2 doesn't equal to D22, D3 doesn't equal to D33, D4 doesn't equal to D44. Hence, if every D1 is not the same as D11, D22, D33, U doesn't equal to S1, U doesn't equal to S2, U doesn't equal to S3, because D1 is not the same as D11, so U doesn't equal to S1. This D2 is not the same as D22, so U doesn't equal to S2. Since D3 doesn't equal to D33, so U doesn't equal to S3. Hence, U doesn't equal to S1, S2, S3. So U doesn't equal to S1, S2, S3, and so on. Hence, if U doesn't equal to each of these S1, S2, S3, then U doesn't belong to the range of F. Then U doesn't belong to the range of F. But U is an infinite bit string. But U is an infinite bit string. It belongs to U. It belongs to the set. It belongs to the set U. But U is an infinite bit string. It belongs to the set U. But U belongs to the bit string. It belongs to the set U. Since U belongs to the codomain, but U doesn't belong to the range, then the codomain is not the same as range. F is not onto. So the range is not the same as codomain. The range of function f is not the same as codomain. The range of function f is not the same as codomain. So f is not onto. If f is not onto, f cannot be a bijection. Hence, f is not a bijection. That's a contradiction. Because we assume if U is countable, there's a bijection f from N to U. So here we find that f is not a bijection, it's a contradiction. It's a contradiction. If we find a contradiction, that means this assumption must be wrong. If we find a contradiction, that means this assumption must be wrong. So U must be uncountable. Therefore, the set U must be uncountable. If U is a subset of S and U is uncountable, then S must be uncountable. Since U is uncountable, and U is a subset of S, then S must be uncountable. If a set has an uncountable subset, the set itself must be uncountable. For any set, if a set has an uncountable subset, then the set itself must be uncountable. So that's a proof that S is uncountable. Number 2, evaluate each of the following sums. First of all, let's keep a few formulas in mind. Summation I from 1 to n, the sum of 1 is n. Summation I from 1 to n, the sum of I is n times n plus 1 over 2. summation I from 1 to n of I square. The sum of I square is n times n plus 1 times 2n plus 1 over 6. Summation I from 1 to n of I cube. That's n squared times n plus 1 squared over 4. And the other one is geometry theory. Summation I from 0 to n. A times r to the power n. A times r to the power n. The formula is a times r to the power of n plus 1 minus a over r minus 1 if r is not 1, because denominator cannot be 0. That's a formula for geometry theory. So memorize these formulas. Now, number 2, part A. Summation k from 1 to 50 of k squared. It looks like this formula here. So we plug in 50 for each n. Plug in 50 for each n. We have 50 times 50 plus 1 is 51 times 2 times 50 plus 1 is 101 over 6. Then here I use my calculator. I get 42,925. Part B. Summation j from 80 to 100. J to the power 3. This formula looks like this formula here. But for this formula, I must start from 1. I must start from 1. If the index starts from 80, what we can do is, I first of all find the sum, j from 1 to 100. But there are too many terms. I subtract the sum, that j from 1 to 79, j to the power 3. I first of all add the terms from 1 to 100. Then I remove the terms from 1 to 79. What's left is the terms from 80 to 100. Then for each of them, I can use the formula here. Plug in the upper limit for each n. I get 100 squared times 101 squared over 4 minus 79 squared times 80 squared over 4. Then I use my calculator. I get 15,516,900. Part C. Find the sum, let I from 20 to 40. 2i squared minus 4i minus 5. So I first of all separate it into three summations. I from 20 to 40, 2i squared minus I from 20 to 40, 4i minus I from 20 to 40 of number 5. Then simplify. I can pull out the constant. Since I is the index, everything other than I is a constant. I can pull out 2, pull out 4, pull out 5. It can be rewritten as the summation 2 in the front, I from 20 to 40. I from 20 to 40. 2i squared. I pull out 2. Pull out 4. Summation I from 20 to 40. Pull out 5. I from 20 to 40. if I pull out 5, I cannot leave it blank here. I need to write 1 as a placeholder. I cannot leave it blank. Next, for summation I from 20 to 40, I can write it as the summation I from 1 to 40, then subtract the summation I from 1 to 19 of I squared. I first will add up the terms from 1 to 40, then remove the terms from 1 to 19. What's left is the term from 20 to 40. Same thing for the second one. I first will add up the sum from I to 40, I from 1 to 40. Then I subtract the terms for I from 1 to 19. Same thing for the last term. I first will add up the sums I from 1 to 40. Then I subtract the sums I from 1 to 19. Then I can use the formula here. I from 1 to 40 of I squared. Let's match this formula here. N times n plus 1 times 2n plus 1 over 6. 40 times 40 plus 1 is 41. Times 2 times 40 plus 1 is 81 over 6 minus the sum I from 1 to 19. Use the formula 19 times 19 plus 1 is 20 times 2 times 19 plus 1 is 39 over 6. Second parenthesis, summation of I from 1 to 40. It looks like this formula here. So I plug in 40 for each n, plug in upper limit for n. 40 times 40 plus 1 is 41 over 2, minus 19 times 19 plus 1, 19 plus 1 is 20. 19 times 20 over 2, minus 5 times the summation I from 1 to 40 of number 1, that's n. So I get 40 minus 19. Then use calculator. Here, use calculator, I get, put this in my calculator, I get 36,715. Type this to my calculator, I get 36,715. Part D. Outer sum I from 0 to 4. Inner sum j from 2 to 5. 2i plus 3j. If both summation has constant limits, have constant limits, we start from the inner sum first. Start from inner sum. I from 0 to 4. J from 2 to 5. When j is 2, I have 2i plus 3 times 2. When j is 3, we have 2i plus 3 times 3. When j is 4, we have 2i plus 3 times 4. When j is 5, we have 2i plus 3 times 5. Then simplify this expression. Leave the outer sum the same, I from 0 to 4. If I combine like terms here, 2i plus 2i plus 2i plus 2i, that's ai. Then here, 2 times 3 is 6. 3 times 3 is 9. 3 times 4 is 12. 3 times 5 is 15. 6 plus 9 is 15. 15 plus another 15 is 30. 30 plus 12 is 42. That's the inner sum. Next, find the sum that I from 0 to 4. If I is 0, we get a times 0 plus 42. If I is 1, we get a times 1 plus 42. If I is 2, we get a times 2 plus 42. If I is 3, we get a times 3 plus 42. If I is 4, you get a times 4 plus 42. Then find the sum. We have 42 plus 42 plus 42 plus 42 plus 42. 42 plus itself 5 times is 210. 8 times 0 is 0, 8 times 1 is 8, 8 times 2 is 16, 8 times 3 is 24, 8 times 4 is 32. So 8 plus 16 is 24. 24 plus 24. 24 plus 24 is 48. 48 plus 32 is 80. 210 plus 80 is 290. That's the sum of this double summation. Next, part E. Part E, the double sum I from 1 to n, j from 1 to I, 2i plus 4j plus 6. The double sum, part E, the double sum, I from 1 to n, j from 1 to I, 2i plus 4j plus 6. Let's try to simplify the inner sum first. So leave an outer sum by itself, I from 1 to n. If I solve an inner sum first, I first of all split the inner sum into 3 summations. J from 1 to I of 2i plus j from 1 to I of 4j, j from 1 to I of 6. Next, I can try to pull out constants, and find the sum for each of them. I from 1 to n. For the first summation here, if I index is j, so everything other than j is considered constant. Is considered a constant. Index is j. Everything other than j is considered a constant. So for the first sum, I can pull out 2i, since both 2i are constant. Index is j. Both 2i are constant. If I pull out 2i, I have j from 1 to I of 1. If I pull out 2i, I put 1 here. I can leave it blank. Second summation, index is j. So number 4 is a constant, I can pull out 4. I treat number 4 as a constant, I can pull out 4. J from 1 to I of j. Last one, number 6 is constant, I can pull out 6. J from 1 to I of 1. If I pull out 6, that's number 1 here. Next, use the formula. Use the formula. Summation of 1. Summation of 1 is an upper limit I. Summation of j. Summation of j is I times I plus 1 over 2. I plug in upper limit into the formula. I times I plus 1 over 2. Summation of I is summation of 1 is the upper limit, which is I. Next, simplify this expression. I have I from 1 to n of 2i squared, 4 divided by 2 is 2 times 2i times I plus 1 plus 6i. If I combine like terms, 2i squared plus 2i squared is 4i squared. Two I plus 6i is 8i. Next, I can split this into 2 summations. I from 1 to n of 4i plus 4i squared. I from 1 to n of 8i. For the first summation, I can pull out 4. For the second summation, I can pull out 8. I have 4 times summation I from 1 to n of I squared plus a times summation I from 1 to n of I. Then use the formula. Summation of I squared is n times n plus 1 over 2n plus 1 over 6. Summation of a times summation of I. That's a times n plus 1 over 2. If I simplify the first term, I have 2 over 3 n times n plus 1 times 2n plus 1. For the second part, a divided by 2 is 4. I have 4n times n plus 1. This is the final answer. Algebraic simplification is not necessary. This is the final answer. It's not necessary to multiply out. It's not necessary to multiply out. That's the final answer. Part F. Outer sum I from 1 to n. Inner sum j from 1 to 2i plus 3. j plus 1. So we start from inner sum first. I from 1 to n. I first of all split the inner sum into two terms. J from 1 to 2i plus 3 of j plus the sum j from 1 to 2i plus 3 of 1. Apply the formula. For the sum of j, use this formula. The sum, the I from 1 to n of I is n times n plus 1 over 2. If we compare these two formulas, we can see that I represents j. So that j represents I. 2i plus 3 represents n. So I plug in 2i plus 3 for each n in the formula. If I plug in, outer sum stays the same. The inner sum here, I plug in 2i plus 3 for each n. I have 2i plus 3 times 2i plus 3 plus 1 is 2i plus 4 over 2. Next, the sum of j from 1 to 2i plus 3 of 1. Compare this formula with the formula I from 1 to n of 1. This formula equal to n. If we compare this formula with this formula, we can see that j represents I, 2i plus 3 represents n. So if I plug in 2i plus 3 for n, I have 2i plus 3. Next, simplify. For the first part, 2i plus 4 here, I can pull out, I can factor 2 out. Then this 2 will cancel 2 on the bottom. So I have 2i plus 3 times I plus 2. Second part is 2i plus 3. Then I try to distribute and combine like terms. If I distribute, I have 2i squared plus 4i plus 3i plus 6 plus 2i plus 3. If I combine like terms, I have 2i squared, 4i plus 3i plus 2i is 9i. And the constant 6 plus 3 is 9. Next, I split the outer sum into 3 summations. I from 1 to n of 2i squared, I from 1 to n of 9i plus I from 9 to n of 9. For the first summation, pull out 2. I from 1 to n of I squared. Second summation, pull out 9. 9 times summation I from 1 to n of I. Third summation, pull out 9. I from 1 to n of 1. Then use the formula for each of them. First one, sum of I squared is n times n plus 1 times 2n plus 1 over 6. The second one, 9 times the sum of I. The sum of I is n times n plus 1 over 2. last one, 9 times the sum of 1. The sum of 1 is n. Then first part I can write it as 1 over 3 times n plus 1 times 2n plus 1. Second part I can write it as 9 over 2 n times n plus 1. The third part is 9n. And algebraic simplification is not necessary. We can leave the answer like this. Algebraic simplification is not necessary. We can leave the answer like this. Number 3. Consider the set of integers from 500 to 2000. First question. How many integers are there in the set? Let's write down all integers first. We have 500, 501, 502, then eventually reach 2000. How many integers are there in the set? This is an arithmetic sequence. These numbers is an arithmetic sequence because the difference between any two consecutive numbers is the same. The difference between any two consecutive numbers is the same. Between 500 and 501, difference is 1. Between 501 and 502, difference is 1. That's called arithmetic sequence. To find out number of terms in arithmetic sequence, take last term minus the first term, divide by the common difference, which is 1. Then add 1. That tells you how many terms are there, which is 2000 minus 500 is 1500. 1500 divided by 1 is 1500. And when we add 1, we get 1501. Since there are 1501 terms, that means there are 1501 numbers in the set. There are 1501 numbers in the set. Part B. How many integers in the set are divisible by 4? How many integers in the set are divisible by 4? Let's write down the sets. Let's write down all numbers that are divisible by 4 first. Numbers divisible by 4. Numbers divisible by 4 are 500, 504, 508, and da 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 da. Last number divisible by 4 is 2000. Last number divisible by 4 is 2000. How many numbers are there in the set? Again, this is arithmetic sequence. The difference between any two consecutive terms is the same. Between 500 and 504, difference is 4. Between 504 and 508, difference is 4. If the difference is the same everywhere, that's called arithmetic sequence. To find out number of terms in the arithmetic sequence, we take last term minus the first term, divide by the common difference. Common difference is 4. Then add 1. 2000 minus 500 is 1500. 1500 divided by 4. 1500 divided by 4. Use my calculator. I get 375. 375 plus 1 is 376. So if there are 376 terms in a set, there are 376 numbers. Part C. How many integers in the set are divisible by 6? First number in the set, first number divisible by 6 is what? Let's test for 500, see if 500 works. 500 divided by 6. Remainder is 2. That means 500 congruent to 2 must 6. 500 congruent to 2 must 6. If I subtract 2 from both sides, I get 498. That's too small. 498 is not in the set. If I subtract 2 from both sides, I can make 0 here. But 500 minus 2 is 298. It's 498. 498 is not in the set from 500 to 2000. So we can subtract 2. I can add 4 to both sides. If I add 4 to both sides, I get 504 on the left side. 2 plus 4 is 6. 6 divided by 6, remainder is 0. So 504 is the first number divisible by 6 in the set. 504 is the first number that divisible by 6 in the set. What's the last number divisible by 6? What's the last number in the set which is divisible by 6? Take 2000 divided by 6. 6 goes to 20 3 times. 18, 20 minus 18, remainder is 2, bring 0 down. 6 goes to 8, goes into 20 3 times. 3 times 6 is 18, remainder is 2, bring 0 down. 6 goes to 20 3 times. 3 times 6 is 18, remainder is 2. So 2000 congruent to 2 mod 6. 2000 congruent to 2 mod 6. If I subtract 2 from both sides, 1998 congruent to 0 mod 6. So that's the last number in the set. That's the first number in the set. The set of numbers that divisible by 6 is 504, 510, 516. Last one is 1998. This is arithmetic sequence. In order to find out how many terms are there, how many numbers are there, take last number divide minus first number. Last number minus first number, divide by the common difference. Common difference here is 6. Then add 1. So 1998 minus 1998 minus 504 is 1494. It's 1494 over 6 plus 1. 1494 divided by 6 is 249. 249 plus 1 is 250. So there are 250 numbers in the set. Because there are 250 terms in a sequence. If there are 250 terms in a sequence, there are totally 250 numbers in a set. So 250 numbers are divisible by 6. 376 numbers are divisible by 4. There are totally 1,501 numbers in a set. Part D. How many integers in a set are divisible by both 4 and 6? In general, if 4 divides x and 6 divides x, then the least common multiple of 4 and 6 divides x. So if x is divisible by 4, x is divisible by 6, x must be divisible by the least common multiple of both numbers. Least common multiple of 4 and 12. Least common multiple of 4 and 6 is 12. So if x is divisible by 4 and x is divisible by 6, then x must be divisible by 12. Then let's try to find out the first number in the set which is divisible by 12. First number in the set divisible by 12. Take 500 divided by 12. Remainder is A. So 500 congruent to A mod 12. 500 congruent to A mod 12. Then if I subtract A from both sides, I get 492 here. 492 is not in the set. 492 is not in the set. So you need to add 4 to both sides. If we add 4 to both sides, on the left side I get 504. On the right side, A plus 4 is 12. 12 divided by 12, remainder is 0. So 504 congruent to 0 mod 12. Which means 504 is the first number in the set. And the last number is 2000. If I take 2000 divided by 12, 12 goes to 20 one time. 1 times 12 is 12. Remainder is A. Bring 0 down. 12 goes into 80 6 times. 6 times 12 is 72. Remainder is A. Bring A down. 12 goes into 80 6 times. 6 times 12 is 72. Remainder is A. That means 2000 congruent to A. 2000 congruent to A mod 12. If I subtract A from both sides, I get 1992 congruent to 0 mod 12. If I subtract A from both sides, 1992 congruent to 0 mod 12. So the last number in the set is 1992. Let's list the set. Let's list the set out. First number is 404. 404 plus 12 is 516. 516 plus 12 is 528, and so on. Last term is 1992. We try to find out how many numbers are there in the set. Again, this is arithmetic sequence. In order to find out how many terms in the sequence, we take last term, 1992, minus the first term, 504, divide by the common difference. Common difference is 12, and add 1. 1992 minus 504 is 1488 over 12 plus 1. 1488 divided by 12 is 124. 124 plus 1 is 125. So there are 125 terms in the sequence, which means there are 125 numbers in the set. Part E. How many integers in the set are divisible by either 4 or 6? Part E. How many integers in the set are divisible by either 4 or 6? Either or. So let A represent the set of numbers, the set of integers. The set of integers from 500 to 2000. Which are divisible by 4. Let B be the set of integers from 500 to 2000, which are divisible by 6. Then A intersection B represents the set of integers from 500 to 2000, which are divisible by both 4 and 6. So A intersection B here represents the set of integers from 500 to 2000, which are divisible by both 4 and 6. Then from part B, part C, part D, we know that set A here, the set of integers divisible by 4 is 376. The set of integers divisible by 6 is 250. The set of integers divisible by both 4 and 6. The set of integers that divisible by both 4 and 6 is 125. Then, part E, we are looking for how many integers are divisible by either 4 or 6. How many integers are divisible by either 4 or 6? We are looking for A union B, set of integers that divisible by either 4 or 6. Then use the formula, that's cardinality of set A plus cardinality of set B minus cardinality of A intersection B. That's set A, and that's set B. A union B involves everything in both sets. That's A union B, which is set A plus set B. But we count the middle part twice. In order to keep it in balance, subtract the middle part. So cardinality of A union B is cardinality of set A plus cardinality of set B minus cardinality of A intersection B. Cardinality of set A is 376. Cardinality of set B is 250. Cardinality of set C is 125. Then use calculator, I get 501. That's the number of integers in a set which is divisible by either 4 or 6. Part F. How many integers in a set are divisible by neither 4 or 6? Divisible by neither 4 or 6. That means the number is not divisible by A and not divisible by B. Neither 4 nor 6. Means element is not in either not in A, is not in A and not in B. Neither divisible by neither 4 nor 6 means the number is not divisible by 4. Number is not divisible by 4 and the number is not divisible by 6. If we use De Morgan's law, this can be rewritten as complement of A union B. That's De Morgan's law. A complement intersection B complement is complement of A union B. This is the universal set. Cardinality of the universal set minus cardinality of A union B. Cardinality of the universal set minus cardinality of A union B. And cardinality of universal set involves all numbers between 500 and 2000. From part A, we know that that's 1501. Elements in A union B. In part E, we found that that's 501. 1501 minus 501 is 1000. So there are 1000 numbers divisible by neither 4 nor 6. Part G. How many integers in the set are divisible by 4 but not 6? How many integers in the set are divisible by 4 but not 6? That's every element in A and not in B. That's number of elements in A and not in B, divisible by 4 but not 6. That can be rewritten as elements in A minus elements in A intersection B. Elements in A but not in B. In Venn diagram looks like this. Elements in A but not in B. We can compute this set by using entire set A minus A intersection B. Take the cardinality of set A minus cardinality of A intersection B. So that's A intersection B complement. Set A refers to the number of integers that's divisible by 4. The set of integers that's divisible by 4. By part B, we know that that's 376 numbers. There are 376 numbers. Minus A intersection B. A intersection B is in a set of numbers. Those are divisible by both 4 and 6. From part D, we know that it's 125. 376 minus 125 is 251. Part H. How many integers in a set are divisible by 6 but not 4? How many integers in a set are divisible by 6 but not 4? We are looking for number of elements in B but not in A. Divisible by 6 but not 4. So similarly, that's the set of B, cardinality of set B minus cardinality of A intersection B. Cardinality of set B from part C, we know that numbers divisible by 6 is 250. A intersection B, number of integers divisible by both 4 and 6. Number of integers divisible by both 4 and 6. From part D, we know that there are 125 such numbers. Then take 250 minus 125, we get 125. So there are 125 numbers divisible by 6, but not divisible by 4. Number 4. Consider all strings with 9 English letters. If repetition are allowed, if repetition are not allowed, how many strings contains the letters X? So string with 9 letters, 1, 2, 3, 4, 5, 6, 7, 8, 9. If repetition are not allowed, how many string contains letter X? So if we want to guarantee the string contains X, we choose one position for X. We choose one position for X and put X later. So for string order matters, we choose one position out of 9. It's permutation. We choose one position out of 9 and put X later. Order matters. Choose one position out of 9. Once I put X here, there are 25 letters left. Once I put X here, there are 25 letters left. And we have 8 different spaces. So we choose 8 space out of, we choose 8 letters out of 25 to fill out these 8 positions. I choose 8 letters out of 25 to fill out these 8 positions, and order matters. This is permutation, order matters. If we simplify, 9 choose 1 is 9. 25 permutation, 25 choose 8 is 25 factorial over 25 minus 8, 17 factorial. That's part A. Part B. If repetition are not allowed, how many strings contains both X and Y? For both X and Y, we must choose 2 positions to put X and Y. We need to choose 2 positions out of 9 to put X and Y. And order matters. If I put Y here, if I put X, if I put Y, if I write Y first, X after, and I write X first, Y after is different. Order matters. It's permutation. I choose 2 positions out of 9 to put X and Y. I choose 2 positions out of 9 to put X and Y. Once I put X and Y on the list, there are 24 letters left. I need to choose 7 more letters. There are 7 more space here. I need to pick 7 more letters out of 24 to fill out the space. So order matters. That's permutation. 24 choose 7. Then simplify. 9 choose 2. 9 choose 2 is 9 factorial over 9 minus 2 is 7 factorial. 24 choose 7 is 24 factorial over 17 factorial. Nine factorial over 7 factorial. After cancellation, we have 9 and 8 left on the numerator. 9 times 8 is 72. 24 factorial over 17 factorial. This number is too big. We can leave it in what it is. And it's 72 times 24 factorial over 17 factorial. Part C. If repetition are not allowed, how many strings contains both X and Y in consecutive position? X and Y in consecutive position, there are 2 possibilities. It's either XY or YX. X and Y in consecutive position, there are 2 possibilities. It's either SY or YX. Since there are 9 positions, there are 9 slots. If I try to put SY or YX in the list, there's only a choice. If I try to put SY on the list, there's only a choice. It could be position 1, 2, 2, 3, 3, 4, up to 8, 9. There are 8 possibilities. There are 8 ways to put SY on the list. So, if S and Y in consecutive order, there are 2 possibilities. It's either SY or YX. The number of ways to put SY or YX on the list is A. There are 8 ways to put SY or YX on the list. Once I put SY on the list, we have 24 letters left. And we must choose 7 more letters to fill out the rest of the space, which is 24, permutation choose 7, 24 choose 7, permutation 24 choose 7, order matters. Since for a string, order matters. then multiply out. 2 times 8 is 16. Permutation 24 choose 7 is 24 factorial over 24 minus 7 is 17 factorial. So the final answer is 16 times 24 factorial over 17 factorial. Part D. If repetition are allowed, how many string contains the letter X? If repetition are allowed, the string may contain 1x, 2x, 3x, 4x, or more x. So if repetition are allowed, string contains x means it contains at least 1x. If we try to calculate directly, it's very hard. Let's try to use set to calculate. Let's try to use cardinality of set to calculate how many string contains x. So let A be the set of strings. Let A be the set of strings that contains x. Let A be the set of strings that contains x. Then A complement will be the set of strings that does not contain x. A complement will be the set of strings that does not contain x. And we know that if I try to find A, cardinality of set A is the universal set. Cardinality of the universal set minus cardinality of element in A complement. If we try to find out cardinality of set A, that's the cardinality of universal set minus cardinality of the set A complement. Universal set represents all strings. Universal set represents the set of all strings, the set of all nine letter strings. The set of all 9 letter strings. So cardinality of universal set, there are 9 letters. Each letter has 26 choice. There are 9 letters. For each letter, we have 26 choice. For each letter, there are 26 choice. So the cardinality of universal set is 26 raised to power 9. 26 times 26 times 26, 9 times is 26 raised to power 9. Cardinality of A complement. A complement is a set of strings that do not contain x. If we can use x, there are 25 choices for each letter. If we can use x, there are 25 choices for each x. So that's 25 to the power 9. And this number is huge. We can live in the weighties. This number is very big. We can live in the weighties. This number is very big. We can live in the weighties. So let's answer for part D. The number of strings that contain letter X. Part E. Part E. If repetition are allowed, how many strings contains either X or Y? If we try to solve it directly, the string contains either X or Y. It could be 1X, 2Y, 3X, 7Y, or 1X, 8Y. There are too many cases to consider. If the string contains X or Y, there are too many cases to consider. So let's think of the complement. We are looking for, suppose let B be the set of string that contains a string of Y. Let B be the set of strings that contains Y. So the cardinality of set A and set B must be the same. Cardinality of set A and set B must be the same. So cardinality of set B must be the same. It's also 26 to the power 9 minus 25 to the power 9. Cardinality of set A and set B must be the same because they are very similar. Then we are looking for the number of strings that contains either X or Y. We are looking for number of strings that contains either X or Y. So let's try to solve it using complement. That's the universal set minus A union B complement. And we know that complement of A union B represent the set of strings that do not contain both X and Y. Complement of A union B represents a set of strings that do not contain both X and Y. If for each place we can use X and Y, there are 24 choices. So the cardinality of the set is 24 raised to the power 9. If we can use X and Y, for each letter there are 24 choices. If we can use X and Y, then for each letter we have 24 choices. Then 24 times 24 times 24 times 24, 9 times. That's 24 raised to power 9. Cardinality of the universal set is 26 raised to power 9. So that's an answer to part E. Next, for part F, if the partition are allowed, how many strings contains both X and Y? Part F, we're looking for number of strings that contains both X and Y. That's A intersection B, cardinality of A intersection B. And we know that A union B, cardinality of A union B is cardinality of A plus cardinality of B minus cardinality of A intersection B. If I solve this equation for cardinality of A intersection B, cardinality of A intersection B can be rewritten as cardinality of A plus cardinality of B minus cardinality of A union B. So use this formula here. Cardinality of A plus cardinality of B minus cardinality of A union B. Then from part D we know that cardinality of A, number of strings that contains X, is 26 to the power 9 minus 25 to the power 9. And similarly, number of string contains letter Y is also 26 to the power 9 minus 25 to the power 9. That's very similar to the first one. Then minus cardinality of A union B. Cardinality of A union B from part E, we know that that's 26 to the power 9 minus 24 to the power 9. Then simplify, combine like terms, we have 26 to the power 9 minus twice 25 to the power 9 plus 24 to the power 9. And this number is huge, it cannot be simplified, we leave it the way it is. This number is huge, we can calculate it, leave it the way it is. Number 5. Consider a set of 7 digits, 0, 1, 3, 5, 6, 7, 9. And a 4-digit number is to be constructed using the numbers in the set without repetition. First question, how many different numbers can be formed? For a 4-digit number, it cannot start with a 0. If we start with a 0, for example, 0, 1, 2, 3, this number is the same as 123. This is a 3-digit number. A 4-digit number cannot start with a 0. This is a 3-digit number. A 4-digit number cannot start with a 0. So keep it in mind. From the set 0, 1, 3, 5, 6, 7, 9, how many 4-digit number can be formed? 1, 2, 3, 4, 4-digit number. When we choose the first digit, we cannot choose 0, but it can be one of these 6 numbers. So there are 6 choices. There are 6 choices for the first number. For the second number, since I used one of the digit already, and it could be 0 here. Second digit could be 0. So again, there are 6 choices. For the third digit, since I used 2 digits out of 7, there are 5 digits left. So we have 5 choices for the third digit. For the fourth digit, there are 4 choices. So multiply out. 6 times 6 times 5 times 4 is 720. Part B. how many such numbers are odd? How many such numbers are odd? If a number is odd, the last digit must be odd. 1, 2, 3, 4. If a number is odd, the last digit must be odd. So how many choices do you have? If a number is odd, the last digit must be odd. So last digit could be 1, 3, 5, 7, 9. There are 5 choices from the last digit. There are 5 choices from the last digit. Then go back to the first digit. Since I use one of an odd number already, for the first digit it cannot be 0. So I have 5 choices from the first digit. I have 5 choices from the first digit. I use one of an odd number already for the last place, and first digit cannot be 0. So I have 5 choices from the first digit. Then from the second digit, since I use 2 digits out of 7, there are 5 digits left. I have 5 choices. For the third place, since I use 3 digits out of 7, there are 4 choices left. So I have 4 choices for the third place. Then for the final answer, multiply out. 5 times 5 is 25. 25 times 4 is 100. 100 times 5 is 500. So 500 such numbers are odd. Part C. How many such numbers are greater than 5,000? How many such numbers are greater than 5,000? If a number is greater than 5,000, the first digit must be 5 or more. If a number is greater than 5,000, the first digit must be 5 or more. So first digit must be 5 or more. It could be either 5, 6, 7, 9. So there are 4 choices from the first digit. It could be either 5, 6, 7, or 9. There are 4 choices from the first digit. Then, since I use 1 digit out of 7, there are 6 digits left. Since I use 1 digit out of 7, there are 6 digits left. So from the second place, there are 6 choices. From the third place, since I use 2 digits already, there are 5 choices. From the last place, since I use 3 digits already, we have 4 choices from the last place. Then for the final answer, multiply out. 4 times 6 is 24. 5 times 4 is 20. 24 times 20 is 480. Part D. How many such numbers are greater than 5,300? If a number is greater than 5,300, then the first digit must be 5 or more. First digit must be 5 or more. If I choose 5 from the first digit, if I pick 5 from the first digit, second digit must be 3 or more. If I choose 5 from the first digit, the choice from the second place must be 3 or more. It must be 3, 6, 7, or 9. There's 4 choices. If I put 5 in the first place, there are 4 choices from the second place. But if I put 6, 7, or 9 in the first place, there's no restriction for the other digits. There are no restriction for other digits. So we must consider this in 2 different cases. Since the choice in the first place affects the choice in the second place, we must consider this in 2 different cases. Since the choice in the first place affects the choice in the second place, we must consider this in 2 cases. So case 1, first digit is 5. Then second digit must be greater than or equal to 3. Case 2, if first digit is not 5, if the first digit is greater than 5, then there's no restriction for the rest of the digits. So if the first digit is 5, there's only 1 choice. There's only 1 5. And second digit must be greater than or equal to 3. Second digit must be greater than or equal to 3. So it could be 3, it could be 6, it could be 7, it could be 9. There are 4 choices for the second place. There are 4 choices for the second place. For the third place, since we used 2 digits already, there are 5 digits left. So we have 5 choices for the third place. And for the fourth place, since I used three digits already, there are 4 choices for the rest. There are 7 digits. If I use 3 digits already, there are 4 choices for the last digit. If the first digit is strictly greater than 5, then it must be 6, 7, or 9. If the first digit is strictly greater than 5, it must be 6, 7, or 9. So there are 3 choices for the first place. There are 3 choices for the first place. Then there's no restriction for the rest. There's no restriction for the rest of the digits. So if I use one of the digit here, there are 6 more digits left. There are 6 more digits left. So we have 6 choices for the second place. Then 5 choices for the third place. 4 choices for the last place. Then multiply, add them up. 4 times 5 is 20. 20 times 4 is 80. 3 times 6 is 18. 5 times 4 is 20. 20 times 18 is 360. So together 80 plus 360 is 440. Number 6. Out of 7 different math books and 12 different physics books, 4 math books and 5 physics books will be selected and arranged on a shelf. First question. In how many ways can a book be arranged? In how many ways can the books be arranged? So there are 2 ways to solve the problem. First method, we can try to set out the position first, then choose the book. Set up the position of the books first. Then choose the book. Let me show you the first method first. So for first method, we try to set out the position for the books first. We try to arrange 9 books. 1, 2, 3, 4, 5, 6, 7, 8, 9. We try to arrange 9 books, and we know that 4 of them must be math books, and 5 of them are physics books. So set out position first. I first of all choose 4 positions out of 9. Choose 4 positions out of 9. Choose 4 positions out of 9. Then for this 4 position, I choose 4 math books out of 7. For this 4 position, I choose 4 math books out of 7. And when we make arrangement for books, order matters. That's permutation. 7 choose 4. When we make arrangement for 4 books, order matters. If I put book 1 here, book 2 here, I put book 2 here, book 1 here. If I switch order, it makes difference. So that's permutation. Order matters. Then for the rest, I choose 5 books for physics. For physics books, I choose 5 books. I choose 5 physics books out of 12. Order matters. That's permutation. 12 choose 5. Then if we simplify, that's 9 factorial. 9 minus 4 is 5 factorial times 4 factorial. 7 factorial. 7 minus 4 is 3 factorial. 12 factorial. 12 minus 5 is 7 factorial times 5 factorial. I can cancel 7 factorial from top and the bottom. So there's no 5 factorial here. It's permutation. There's no 5 factorial here. It's permutation. Cancel 7 factorial. What's left is 9 factorial, 12 factorial over 5 factorial, 4 factorial, 3 factorial. If this number is small, you can use calculator to get an answer. If this number is small, you can use calculator to get an answer. Part B. In how many ways can a book be arranged if math and physics book alternate? In how many ways can a book be assigned if the math and physics book alternate? If they alternate, that means there's only one possible order. If they are alternate, there's only one possible order. We have more physics book, fewer math book. It must be physics, math, physics, math. It must be exactly in this order. Physics, math, physics, math. Last book must be physics. It must be exactly in this order. So the position is fixed. The position is fixed. We choose 4 math book out of 7. Then we choose 5 physics book out of 12. Then use the formula. That's 7 factorial, 7 minus 4 is 3 factorial times 12 factorial, 12 minus 5 is 7 factorial. Cancel 7 factorial. Answer is 12 factorial over 3 factorial. Part C. Part C. In how many ways can a book be arranged? If a math book must be at the beginning of the shift. In how many ways can a book be arranged? If a math book must be in the beginning of the shift. So if we want a math book in the beginning of the shift, so if the math book must be in the beginning of the shift, for the rest, for the other 8 book here, 3 of the book must be math. Since there are totally 4 math book. If I put math book in the beginning, for the rest, 3 of the book must be math book. 3 out of this 8 book must be math books. 3 out of these 8 books must be math books. So we need to choose 3 position out of A to put math book here. So let's A choose 3. We choose 3 position out of A to put math book here. Then once I choose a position, I assign 4 math book out of 7. Once I choose the position for math book, I choose 4 math book out of 7. Out of 4 math book out of 7. Order matters. That's permutation. 7 choose 4. Then we need to choose 5 more books, 5 more physics books out of 12. Permutation 12 choose 5. Then multiply out. A choose 3 is A factorial. This is combination. A choose 3 is A factorial. A minus 3 is 5 factorial times 3 factorial. Permutation 7 choose 3 is 7 factorial. 7 minus 4 is 3 factorial. 12 factorial. 12 minus 4 is 7 factorial. Cancel 7 factorial from top and the bottom. The final answer is A factorial times 12 factorial over 5 factorial times 3 factorial times 3 factorial. That's part C. Part D. Part D. In how many ways can a book be arranged? If a math book must be at the beginning and 2 physics books must be at the end of the shift. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 books. 1 math book must be in the beginning. 2 physics books must be at the end. In the middle, there are 6 books. In the middle, there are 6 books. There are 6 books in the middle. 3 of the books must be math, and 3 of these books must be physics. In the middle, there are 6 books. 3 of the books must be math. 3 of the books must be physics. So we choose 3 position for math books. That's permutation, that's combination. 6 choose 3. We chose 3 position out of 6 to put math books. Then next, I choose 4 math book out of 7 and put it here. Next, I chose 5 physics books, put it here. Choose 5 physics books out of 12. Then simplify. 6 factorial over 3 factorial times 3 factorial. 7 factorial over 3 factorial. 7 minus 4 is 3. 12 factorial over 7 factorial. 12 minus 5 is 7. Then I can cancel 7 factorial. And the final answer is 6 factorial times 12 factorial. 3 factorial times 3 factorial times 3 factorial. Part E. Part E. In how many ways can a book be arranged if all math books must remain together? In how many ways can a book be arranged if all math books must remain together? 1, 2, 3, 4, 5, 6, 7, 8, 9. We try to put all 4 math books. We try to choose 4 math books out of 7. If we try to put all 4 math books together, it could be either in position from 1 to 4. Could be in position from 2 to 5, 3 to 6. How many possibilities are there? So math book may occupy position 1, 2, 3, 4. They may occupy position 2, 3, 4, 5. They may occupy last possibilities 6, 7, 8, 9. They may occupy position 6, 7, 8, 9. So you can see that there are 6 possibilities. There are 6 possibilities to put 4 math books together. There are 6 ways to put 4 math books together. There are 6 ways to put 4 math books together. These 4 math books may occupy positions 1, 2, 3, 4, 2, 3, 4, 5, up to 6, 7, 8, 9. Next, I need to choose 4 math books out of 7. Next, I choose 4 math books out of 7, put it here. Then I choose 5 math books, 5 physics books out of 12, put it in the rest of the place. Next, 6 times 7 factorial over 3 factorial times 12 factorial over 7 factorial. Cancel 7 factorial. That's 6 times 12 factorial over 3 factorial. And 3 factorial is 6, and so it's 12 factorial. For problem number 6, a different technique is that we can choose the books first, then make arrangement. A different technique for problem number 6 is that we can choose the books first, then make arrangement. Second technique, we choose the books first, then make arrangement. So part A, in how many ways can we choose 4 math books and 5 physics books and arrange them on a shelf? I first of all choose 4 math books out of 7. That's combination. I first of all choose 4 books out of 7. Order doesn't matter. I first of all choose 4 math books out of 7. Then I choose 5 physics books out of 12. Now I have a total of 9 books. Next, I make arrangement and put it on the shelf. I make arrangement for 9 books. The number of ways to make arrangement for 9 books is 9 factorial. The number of ways to make arrangement for 9 books is 9 factorial. So I choose the books first, then make arrangement, put it on the shelf. That's the second technique. If I simplify, I have 7 factorial over 4 factorial times 3 factorial times 12 factorial over 7 factorial times 5 factorial times 9 factorial. If we simplify, 7 factorial can cancel, 7 factorial can cancel. We have 12 factorial times 9 factorial 4 factorial times 3 factorial times 5 factorial, which is exactly the same. Part B. In how many ways can a book be arranged if math and physics books are alternated? So let's choose the books first. We choose 4 math books out of 7, 5 physics books out of 12. Then, since the positions are fixed, the book must be alternated. It must be math, physics, math, physics, math, physics, math, physics, math, physics. Let's make arrangement for 4 math books first. Let's make arrangement for these 4 math books first. The number of ways to make arrangement for 4 math books is 4 factorial. 4 choice here, 3 choice here, 2 choice here, 1 choice here. Physics book must come first. 4 choice, 3 choice, 2 choice, 1 choice. So the number of ways to make arrangement for 4 math books is 4 factorial. The number of ways to make arrangement for 5 physics books is 5 factorial. 5 choice, 4 choice, 3, 2, 1. Then if we simplify, that's 7 factorial over 4 factorial, 3 factorial times 12 factorial, 7 factorial, 5 factorial times 4 factorial times 5 factorial. I can cancel 4 factorial, cancel 5 factorial, cancel 7 factorial. What's left is 12 factorial over 3 factorial. We get exactly the same answer. Part C. In how many ways can a book be arranged if a math book must be at the beginning of the shaft? So let's choose the books first. Then make arrangement. If we choose the books first, that's 7 choose 4. We have this many ways to choose 4 math books out of 7. 12 choose 5. We have this many ways to choose 5 physics books out of 12. Next, if in the first place must be a math book, 1, 2, 3, 4, 5, 6, 7, 8, 9. If in the first place must be a math books, we choose 1 math book and put it here. If in the first place must be a math book, we choose 1 math book and put it here. It's permutation 5 choose 1. We choose 4 math book and put it here. That's permutation 4 choose 1. We first of all choose 4 math book out of total of 7. Then we choose 1 math book, put it here. We choose 1 math book, put it in the front of the row. There are 4 choices. We choose 1 math book, put it in the front of the row. That's permutation 4 choose 1. When we make arrangement, order matters. So we use permutation 4 choose 1, put it here. Then once I put a math book here, I make arrangement for the other 8 books. Once I put 1 math book here, I have 8 books left. I can arrange these 8 books in any orders. So the number of ways to make arrangement for 8 books is 8 factorial. So when I choose 4 math books, 5 physics books, I have 9 books. Since I want a math book in the front, I choose 1 math book, put it in the front. Then I have 8 books left. This 8 book can be put in any order. The number of ways to arrange 8 books is 8 factorial. So multiply out. If I simplify, I have 7 factorial over 4 factorial over times 3 factorial, 12 factorial over 7 factorial times 5 factorial. Permutation 4 choose 1 is 4 factorial over 4 minus 1, 3 factorial times 8 factorial. If we simplify, 4 factorial can cancel, 7 factorial can cancel. We have 12 factorial times 8 factorial over 3 factorial, 5 factorial, 3 factorial. We get exactly the same answer. Part D. In how many ways can a book be arranged if a math book must be in the beginning and 2 physics books must be at the end of the shaft? So, part D. we choose the books first. We first of all choose 4 math books out of 7, 5 physics books out of 12. Next, I want a math book in the front. So I choose 1 math book, put it in the front. There are totally 4 math books. I choose 1, arrange it in the front. That's permutation, order matters. Then next, I choose 2 physics books. I arrange 2 physics books to put in the back. There are totally 5 physics books. I choose 2 physics books to put it at the end. So this 5 choose 2. Order matters, it's permutation. When we're making arrangement, order matters, it's permutation. Next, in the middle, we can see that there are 6 books in the middle. Then there are 6 books in the middle. These 6 books can be in any order. The number of ways to arrange 6 books is 6 factorial. The number of ways to arrange 6 books is 6 factorial. The number of ways to arrange 6 books is 6 factorial. Then simplify. 7 choose 4 is 7 factorial, 4 factorial, 3 factorial. 12 choose 5 is 12 factorial, 7 factorial, 5 factorial. 4 choose 1 is 4 factorial over 3 factorial. 5 choose 2 is 5 factorial over 3 factorial times 6 factorial. If we simplify, 4 factorial on the top and the bottom can cancel. 7 factorial can cancel. 5 factorial can cancel. What's left is 12 factorial times 6 factorial over 3 factorial 3 times. That's the same answer. Part E. In how many ways can a book be arranged if all math books must remain together? So part E, same thing, we choose the books first. We first of all choose 4 math books out of 7, 5 physics books out of 12. Then I have 9 books. If we try to combine 4 math books together, the number of ways to arrange these 4 books, is 4 factorial. The number of ways to arrange these 4 books is 4 factorial. Next, we have 5 physics books. P1, P2, P3, P4, P5. If these 4 math books must be together, so we consider this is one object. And this physics book may be in different order. These physics they may not go together. So we consider there are 6 objects. If 4 math books must be together, we consider this is one object. And each physics book is considered one object. So together there are 6 objects. The number of ways to arrange 6 objects is 6 factorial. The number of ways to arrange 6 objects is 6 factorial. Then we can simplify. 7 factorial over 4 factorial over times 3 factorial. 12 factorial over 7 factorial times 5 factorial times 4 factorial times 6 factorial. If we simplify, cancel 4 factorial, cancel 7 factorial. What's left is 12 factorial times 6 factorial over 3 factorial times 5 factorial. And 6 factorial over 5 factorial is 6. 6 factorial over 5 factorial is 6. And so it's 6 times 12 factorial over 3 factorial. Number 7. In a supermarket, assume there are 20 different types of drinks, including water, Sprite, Coke, etc. First question. How many ways are there to choose 30 bottles of drinks? Since we can choose each drink multiple times, this is a problem about multi-choose. Suppose there are n categories. The number of ways to choose r objects out of n category is n plus r minus 1 choose m minus 1. The number of ways to choose R category, to choose R objects out of n category is m plus R minus 1, choose m minus 1. Or this formula is equivalent to m plus R minus 1, choose R. That's the formula for multi-choose. It represents the number of ways to choose R objects out of n category. The number of ways of choosing R objects out of n category. First question. In how many ways can we choose 30 bottles of drinks out of 20 different types? Let's 20 multi-choose 30. 20 multi-choose 30. We are choosing 30 objects out of 20 category. Use the formula m plus R minus 1 is 59. Choose m minus 1. m minus 1 is 19. So it should be 49 choose 19. 20 plus 30 is 49. Is 50. 50 minus 1 is 49. 49 choose 19. Then this is combination. 49 factorial, 40 minus 19 is 30 factorial times 19 factorial. Part B. How many ways are there to choose 30 bottles of drinks, including at least 3 bottles of water? In order to guarantee 3 bottles of water, we need to choose. We pick 3 bottles of water first. Then we need to choose 27 more bottles. So in order to guarantee at least 3 bottles of water, we first of all choose 3 bottles of water first. We pick 3 bottles of water first. Then we need to choose 27 more bottles of drinks out of 20 category. So choose 3 bottles of water first. Then we need to choose 27 more bottles of drinks out of 20 category. We may get more waters, but we need to guarantee at least 3 water. We pick 3 bottles of water first. Then we choose 27 more bottles of drinks out of 20 category. Use the formula. That's 20 plus 27 minus 1 is 46. 20 minus 1 is 19. So you get 46 choose 19. 46 choose 19 is 46 factorial. 46 minus 19 is 27 factorial times 19 factorial. That's part B. Part C. How many ways are there to choose 30 bottles of drinks, including exactly 2 bottles of water and at least 4 bottles of Sprite? So, to guarantee exactly 2 bottles of water and at least 4 bottles of Sprite, we first of all pick 2 bottles of water and 4 bottles of Sprite. We first of all pick 2 bottles of waters and 4 bottles of Sprites. We pick 6 bottles of drinks. We pick a total of 6 bottles of drinks first. Then we need to choose 24 more bottles of drinks. To guarantee 2 bottles of water and 4 bottles of Sprite, we pick these 2 bottles of water first. Then we pick 4 bottles of Sprite. That means we choose a total of 6 bottles of drinks first. If we choose a total of 6 bottles of drinks first, we need to pick 24 more bottles. Now, since we want exactly 2 bottles of water, we cannot choose water anymore. But we may choose more Sprite. But we cannot choose any more water. So there are 19 categories left. There are totally 20 categories. Since I cannot choose water anymore, there are 19 categories left. So we choose 24 bottles of drinks out of 19 categories. We may choose more Sprites. So we choose 24 bottles of drinks out of 19 categories. Use the formula. 19 plus 24 minus 1 is 42. And 19 minus 1 is 18. Use the formula. That's 42 factorial over 42 minus 18 is 24 factorial. times 18 factorial. That's part C. Part D. How many ways are there to choose 30 bottles of drinks, including at most 2 bottles of Cokes? How many ways are there to choose 30 bottles of drinks, including at most 2 bottles of Coke? At most 2 bottles of Coke means it could be either 0 bottle of Coke, 1 bottle of Coke, or 2 bottles of Coke. So there are 3 cases. It could be 1 bottle of Coke, it could be 0 bottle of Coke, it could be 1 bottle of Coke, it could be 2 bottles of Coke. There are 3 cases. It could be at most 2 bottles of Coke, means it could be 0 bottle of Coke, 1 bottle of Coke, or 2 bottles of Coke. So there are 3 cases. First case, if we choose 0 bottle of Coke, means we don't choose any Cokes. If we don't choose any Cokes, that means Coke is not available. We can't choose Coke. Coke is not available. There are 19 categories. If we don't choose Coke, means Coke is not available. There are 19 categories. Then we choose 30 bottles of drinks out of 19. Case 2. If we choose only 1 Coke, pick 1 Coke first. Then we cannot pick any more Coke. So there are 19 categories left. Pick 1 Coke first. Then we cannot choose any Coke. Since we picked 1 Coke already, there are 29. We need to choose 29 more bottles of drinks. Since I picked 1 bottle of Coke already, I need to choose 29 bottles of drinks. The third case, if I want to choose exactly 2 bottles of Coke, I pick 2 bottles of Coke first. Then Coke, I cannot choose any more Coke. Coke is not available anymore. There are 19 categories available. Since I choose 2 bottles of Coke already, I need to choose 28 more drinks. 28 more bottles of drinks. Then use the formula. 19 to 30. 19 plus 30 minus 1 is 48. 19 minus 1 is 18. 48 is 18 plus 19 plus 29 minus 1 is 47. 19 minus 1 is 18 plus 19 plus 28 minus 1 is 46, and 19 minus 1 is 18. Then use the formula. 48 plus 18 is 48 factorial, 30 factorial, 18 factorial. 47 choose 18 is 47 factorial. 47 minus 18 is 29 factorial times 18 factorial. 46 factorial over 28 factorial over 18 factorial. These numbers are huge. We leave it the way it is. Part D, Part E. Part E. How many ways are there to choose 30 bottles of drinks, including at least 1 bottle of water, exactly 2 bottles of Sprite, at most 3 bottles of Coke? How many ways are there to choose 30 bottles of drinks, including at least 1 bottle of water, exactly 2 bottles of Sprite, at most 3 bottles of Coke? So at most 3 bottles of Coke. Let's consider these 4 cases. It could be 0 bottle of Coke, 1 bottle of Coke, 2 bottles of Coke, or 3 bottles of Coke. So there are 3 cases. Consider this problem in 3 cases. So 0 Coke, 0 bottle of Coke, 1 bottle of Coke, 2 bottles of Coke, or 3 bottles of Coke. There are 3 cases. First case, 0 Coke. We need to choose at least 1 bottle of water, 2 bottles of Sprite, and 0 bottle of Coke. So pick 1 bottle of water first, 2 bottles of Sprite first. If we pick 1 bottle of water, 2 bottles of Sprite, we need to choose 27 more bottles of drinks. If we pick 1 bottle of water, 2 bottles of Sprite, we need to choose 20 more bottles of drinks. But here, since we want exactly 2 bottles of Sprite, we pick 2 bottles of Sprite already. We cannot choose Sprite anymore. And since we want 0 bottle of Coke, we cannot choose Coke anymore. We cannot choose any Coke. So there are 18 categories. We may have more waters. We may choose more waters. We may choose more waters. So water is still available. But Sprite is not available. Coke is not available. We have 18 categories, 18 more categories. We choose 27 bottles of drinks out of 18 categories. Case 2, 1 Coke. 1 Coke. I choose 1 bottle of water first, 2 bottles of Sprite first, and 1 bottle of Coke first. I choose 4 bottles of drink already, so I need to choose 26 more bottles of drinks. I choose 4 bottles of drink already. I need to choose 26 more bottles of drinks. And since I pick 1 bottle of water already, I may pick more water, so water is still available. But if I pick 2 bottles of Sprite already, Sprite is no longer available. Sprite is no longer available. And I choose 1 bottle of Coke already. Coke is no longer available. So there are 18 different categories left. We choose 26 bottles of drinks out of 18 categories. Case 3, 2 bottles of Coke. If we are getting exactly 2 bottles of Coke, let me choose 1 bottle of water first. 1 bottle of water, 2 bottles of Sprite, and 2 bottles of Coke. I choose 5 bottles of drinks already. I need to choose 25 more bottles of drinks. And Sprite is no longer available. Coke is no longer available. There are 18 categories left. So I choose 25 more bottles of drinks out of 18 categories. Last case. 3 bottles of Coke. We are choosing exactly 3 bottles of Coke. Let me choose 1 bottle of water first, and 2 bottles of Sprite first. Then exactly 3 bottles of Coke first. 1, 2, 3. I already choose 6 bottles of drinks. That means I need to choose 24 more bottles of drinks. I need to choose 24 more bottles of drinks. Since I want exactly 2 bottles of Sprite, I picked 2 bottles of Sprite already. Sprite is no longer available. In the third case, we want exactly 3 bottles of Coke. Since I chose 3 bottles of Coke already, Coke is no longer available. So there are 18 categories left. Since Sprite and Coke they are no longer available, we have 18 categories left. Then we choose 24 bottles of drinks out of 18 categories. Then use the formula. 18 choose 27. We use 18 plus 27 minus 1 is 44. 18 minus 1 is 17, so that's 44 choose 17. Next, we use 18 plus 26 minus 1, that's 43. 18 minus 1 is 17. Next, we use 18 plus 25 minus 1 is 42. 18 minus 1 is 17. Next, 18 minus 24 plus 1, 18 plus 24 minus 1 is 41. 18 minus 1 is 17. Then those are combinations. Use the formula 44 factorial over 27 factorial times 17 factorial plus 43 factorial. 43 minus 17 is 26 factorial times 17 factorial plus 42 factorial. 42 minus 17 is 25 factorial times 17 factorial. Next, 41 factorial. 41 minus 17 is 24 factorial times 17 factorial. This number is huge. We can live in the weighties. This number is huge. We can live in the weighties. Number A, part A. How many bit strings of length 10 contains 2 consecutive zeros? Let's try to set out a problem using recurrent relation. Let an represent the number of bit strings with length n. That contains two consecutive zeros. We try to find a recurrent relation for an. So, given a string of length n, given a bit string of length n, let's consider all possible cases. Given a bit string of length n, so since we are looking for two consecutive zeros, let's focus on the last two digits. How many possible cases for the last two digits? The last two digits could be either 11, 01, 10, or 00. For any bit strings, the last two digits has four cases. Could be either 11, 01, 10, 00. For the first two cases, the last digit is a 1. For the first two cases, last digit is a 1. So the bit string ends with a 0. So it ends with a 1. For the first case, for the first two lines, the bit string ends with a 1. For the first two cases, the bit string ends with a 1. For the second case, for the second and third case, we cannot consider these two cases together because in this case, it guarantees two consecutive zeros. But in the third case, it doesn't guarantee two consecutive zeros. So we cannot consider these two cases together. We must consider this as two different cases. Second case, the string ends with 1, 0. The string ends with 1, 0. Last case, the string ends with 2 zeros. Let's consider these three cases individually. Case 1. The string ends with a 1. Given a string of length n, the string ends with a 1. Consider a string of length n. So there are n digits here. If last digit is 1, then two consecutive zero must come from here. It cannot be in the last digit. Two consecutive zero must come from the first n-1 digits. So there are n-1 digits here. Two consecutive zero must come from here. So the number of the number of bit string with length n minus 1 with two consecutive zeros is a sub n minus 1. So the number of such bit strings that contains two consecutive zeros is a sub n minus 1. That's the first case. If the string contains two consecutive zeros, it must belong to here. It must belong to the first n minus 1 digits. So the number of way to have the number of bit strings of length n minus 1 that contains two consecutive zeros is a sub n minus 1. That's case 1. Case 2. Case 2. The string ends with 1 0. Given a string of length n that contains two consecutive zeros. Case 2. If the string ends with 1 0, Case 2. If the string ends with 1 0, so the last two digit must be 1 0. If the string has length n, it must be n minus 2 0. It must be n minus 2 digits in the front. If the string has length n, it must be n minus 2 digits in the front. If the string contains two zeros, these two zeros cannot be in the last place. It must be in the front. If the string contains two zeros, these two zeros cannot be at the end. It must be in the front. So that's a string of length. That's a bit string of length n minus 2 contains two consecutive zeros. The number of such string is a sub n minus 2. The number of such string is a sub n minus 2. So the number of such bit strings that contains two consecutive zeros is a sub n minus 2. If this string contains two zeros, it must be in front of this 1. And in front of 1, that's a bit string of length m minus 2. The number of string with length m minus 2 contains a consecutive zero is a sub m minus 2. That's case 2. Case 3. This string may end with two zeros. If a string ends with two zeros, then it guarantees, if there's two zeros at the end, no matter what we put in the front, it guarantees the string always have two zeros. No matter what we put in the front, it guarantees the string always have two consecutive zeros. So Since each place has two choices, it could be either 0 or 1, 0 or 1, 0 or 1. Since each place has two choices, and there are m minus 2 digits, we have a total of 2 raised to m minus 2 choice for the strings. We have a total of 2 raised to m minus 2 such strings. Then the number of such bit string that contains 2 consecutive zeros is n 2 raised to the power of m minus 2. The number of such bit string that contains 2 consecutive zeros is 2 raised to the power of m minus 2. If the last 2 digits are zeros, no matter what we put in the front, for each digit, no matter what we put in the front, it guarantees the string has 2 consecutive zeros. So for each digit, there are 2 choices. It could be either 0 or 1, 0 or 1, 0 or 1. There are m minus 2 digits. So we have 2 times 2 times 2, m minus 2 times. We have this many digits. We have this many bit strings that contains 2 consecutive zeros. So we have 3 cases here. So a sub n, the number of bit string that contains 2 zeros. It could be either, it may end with a 1, end with a 1 0, or end with 0 0. That's the number of bit strings on each case. So we add them up. A sub n equal to a sub n minus 1 plus a sub n minus 2 plus 2 raised to n minus 2. This formula, since the index cannot be negative, this formula only works if n is greater or equal to 2. Then we consider n equal to 0, n equal to 1 is a special cases. What's a sub 0? A sub 0 represents number of bit strings that has length 0, which contains 2 consecutive zeros, which is impossible. A bit string with length 0 is an MP string. MP string won't contain 2 consecutive zeros, so the number of such string is 0. A sub 1, that's the number of bit string of length 1. If a bit string has length 1, it could be it's a string of either 0 or 1. String of 0 doesn't contain 2 consecutive zeros, and similarly, string of 1 doesn't contain 2 consecutive zeros. So there are no such string. No string with length 1 contains 2 consecutive zeros. No string with length 1 contains 2 consecutive zeros. So A0 is 0, A1 is 0. We try to find how many bit string of length 10 contains 2 consecutive zeros. That means we are looking for A sub 10. So this is a recurrent relation. We must compute each one by one. There's no shortcut unless we find a closed form. But so far, let's find this one by one. A1, An equal to Am minus 1 plus A sub m minus 2 plus 2 to the power of m minus 2 if n is greater or equal to 2. A0 equal to 0, A1 equal to 0. That's a recurrent relation. Let's compute this one by one. There's no shortcut. A0 is 0, A1 is 0, A2 is, I substitute 2 for each n. A1 plus A0 plus 2 to the power of 0. 0 plus 0 plus 0 plus 0 plus 1 is 1. A3 equal to, I plug in 3 for each n, equal to A2 plus A1 plus 2 to the power 1. A2 is 1. A1 is 0. 2 to the power 1 is 2. 1 plus 2 is 3. A4, it's A3 plus A2 plus 2 to the power 2. A3 is 3, we just found. A2 is 1. 2 to the power 2 is 4. 3 plus 1 plus 4 is 8. 8 to the power 5 is A4 plus A3 plus 2 to the power 3. A4 is A. A3 is 3. 2 to the power 3 is A. That's 19. A sub 6. It's A5 plus A4 plus 2 to the power 4. A5 is 19. A sub 4 is A. 2 to the power 4 is 16. Adding up, we have 43. A7, that's A sub 6 plus A sub 5 plus 2 to the power 5. A sub 6 is 43. A sub 5 is 19. 2 to the power 5 is 32. That's 19 plus 32 is 51. 51 plus 43 is 94. A sub A is A sub 7 plus A sub 6 plus 2 to the power 6. A sub 7 is 94. A sub 6 is 43. 2 to the power 6 is 64. If we add them up, that's 94 plus 64 is 158. 158 plus 43 is 201. A sub 9 is A to the power A sub A plus A sub 7 plus 2 to the power 7. A sub A is 201. A sub 7 is 94. 2 to the power 7 is 128. Adding up, we get 423. Last one, A sub 10 is A sub 9 plus A sub 8 plus 2 to the power 8. That's 423 plus 201 plus 256. Adding up, we got 880. That's an answer. Number 8, part B. How many bit string of length 10 contains 3 consecutive zeros? Let's try to solve the problem using recurrent relations. The AN represents the number of bit strings. With length n. That contain 3 consecutive zeros. The A sub n represents number of bit strings with length n that contains 3 consecutive zeros. Given a bit string, let's try to find the current relation for A sub n. Let's try to find the current relation for A sub n. So let's set out a problem. Given a bit string of length n, that contains 3 consecutive zeros. That contains 3 consecutive zeros. Let's look at the last 3 digits, since we try to focus on 3 consecutive zeros, let's look at the last 3 digits. The last three digits, it may be 111, 101, 011, 001, or it may be 110, 100, 100, 010, 100, or 000. The last 3 digits has 8 possibilities. The last 3 digits has 8 possibilities. For the first 4 cases, the last digit is 1. So for the first 4 cases, it ends with a 1. For the last 4 cases, the bit string ends with a 1. For these 2 cases here, it ends with 10. For these 2 cases here, it ends with 10. The bit string ends with 10. For this case here, it ends with 100. For the last case, it ends with 3 zeros. Let's consider these cases individually. Case 1, case 2, case 3, case 1, case 2, case 3, case 4. Let's consider these 4 cases individually. Case 1, case 2, case 3, case 4. Let's consider these 4 cases individually. Case 1. The string ends with a 1. The bit string ends with a 1. Case 1. The string ends with a 1. So let's consider a string of length n. 1, 2, 3, 4, 5 up to n. Let's consider a string of length n. There are n digits here. If we end with a 1, then the 3 consecutive zeros must be in front of 1. The 3 consecutive zeros must come in front of 1. That's a bit string of n-1 digits. And we have if a string contains 3 consecutive zeros, it must contain in front of 1. So the number of string with length 1 that contains 3 zeros. The number of bit string of length n-1 contains 3 zeros is a sub n-1. So the number of such bit strings that contain 3 consecutive zeros is a sub n-1. The number of such bit strings that contains 3 consecutive zeros is a sub n-1. If this string contains 3 consecutive zeros, it must come in front of 1. This is a bit string of length n-1. The number of bit string with length n-1 has 3 consecutive zeros is a sub n-1. That's case 1. Case 2. The bit string ends with 1, 0. If the bit string ends with 1 0, if the bit string ends with 1 0, the number of digits in front of 1 is n minus 2 digits. If the bit string ends with 1 0, the number of digits in front of 1 is n minus 2 digits. And if this bit string contains 3 consecutive zeros, it cannot come after 1. It must come in front of 1. If this bit string contains 3 consecutive zeros, it must come in front of 1. So, if it contains 3 consecutive zeros, it must be here. It must be contained in a string of n minus 2 digits. So, the number of string of length n minus 2 that contains 3 consecutive zeros is a sub n minus 2. The number of string of length n minus 2 that contains 3 consecutive zeros is a sub n minus 2. So the number of such bit strings that contain 3 consecutive zeros is a sub n minus 2, because this is a string of length n minus 2. If this entire string contains 3 zeros, it must come in front of 1. So 3 consecutive zeros must be here. This is a string of length n minus 2. The number of such string is a sub n minus 2. That's case 2. We have this many strings that contain 3 consecutive zeros. Case 3. The string ends with 100. The bit string ends with 100. If the bit string ends with 100, we have m minus 3 digits in front of 1. We have m minus 3 digits in front of 1. If this string contains 3 consecutive zeros, it must come in front of 1. It cannot go after 1. It must come in front of this 1. In front of 1, this is a bit string of m minus 3 digits. That's a bit string of length m minus 3. The number of bit strings of length m minus 3 that contains 3 consecutive zeros is a sub m minus 3. So the number of such bit string here is a sub m minus 3. Number of bit strings that contains the number of such bit strings that contains three consecutive zeros is a sub m minus 3. The number of bit strings that contains 3 consecutive zeros is a sub m minus 3. Case 4. The bit string ends with 000. The bit string ends with 000. If the bit string ends with 000, it doesn't matter what we put in the from. This string always contains 3 consecutive zeros. If the string contains 0, 0, 0, no matter what we put in the from, it always has 3 consecutive zeros. So there are 2 choices for the first digit, 2 choices for the second digit, 2 choices for each digit. Multiply out. There are n minus 3 such digits. So we have 2 to the power of n minus 3. We have this many number of digits. We have this many number of digits that contains 3 consecutive zeros. So if the bit string ends with 3 zeros, the number of such bit string that contain 3 consecutive zeros is 2 to the power of n minus 3. Those are 4 different cases. Then add them up. So an is a sub n minus 1, case 1 plus case 2, a sub n minus 2, plus a sub n minus 3, plus last one is 2 to the power of n minus 3. 2 to the power of n minus 3. This formula only, since the index cannot be negative, this formula only works for n greater or equal to 3. This formula only works when n is greater or equal to 3. When n is less than 3, we consider there are special cases. A sub 0 is 0. If a string has length 0, the number of string contains 3 consecutive zeros is 0. That's impossible. If a string has length 1, the number of string contains 3 consecutive zeros is also impossible. That's 0. That's impossible. If a string has length 2, the number of such string has 3 consecutive zeros is impossible. If there's only 2 digits, we won't have 3 consecutive zeros. That's also 0. A sub 0 is 0, a sub 1 is 0, a sub 2 is 0. Then the problem is asking how many bit string of length 10 contains 3 consecutive zeros. So for this problem, we are looking for a sub 10. This is a recurrent relation. Since we don't know the closed formula, since we don't know the closed form, we must compute this one by one from A0, A1, A2 up to A10. A0 is 0, A1 is 0, A2 is 0. For A3, we substitute 3 for each n. We get A sub 2 plus A sub 1 plus A sub 0 plus 2 to the power of 3 minus 3 is 0. A sub 2 is 0, A sub 1 is 0, A sub 0 is 0, A sub 2 to the power 0 is 1. So A sub 3 is 1. A sub 4 is A3 plus A2 plus A1 plus 2 to the power 1. That's 1 plus 0 plus 0 plus 2, which is 3. A sub 5 is A sub 4 plus A sub 3 plus A sub 2 plus 2 to the power 2, which is 3 plus 1 plus 0 plus 2 squared is 4, which is A. A sub 6 is A sub 5 plus A sub 4 plus A sub 3 plus 2 to the power 3. That's A plus 3 plus 1 plus 2 to the power 3 is A. A plus A is 16. 16 plus 4 is 20. A sub 7 is A sub 6 plus A sub 5 plus A sub 4 plus 2 to the power 4. 20 plus A plus 3 plus 16. That's 31. 31 plus 16 is 47. A sub A, that's A sub 7 plus A sub 6 plus a sub 5 plus 2 to the power of 5. A sub 7 is 47, a sub 6 is 20, a sub 5 is 8, 2 to the power of 5 is 32. I get 107. A sub 9 is a sub a plus a sub 7 plus a sub 6 plus 2 to the power 6. That's 107 plus 47 plus 20 plus 2 to the power 6 is 64. Adding up, I get 238. Next, I have a sub 10 equal to a sub 9 plus a sub 8 plus a sub 7 plus 2 to the power 7. That's 238 plus 107 plus 47 plus 128, which is 520. That's an answer. There are 520 such bit strings has of length 10 has 3 consecutive zeros. Number 8, part C. Suppose you only have $1, $2, $5 bills. In how many different ways can you make deposit of $10? So same thing, let's try to use the current relation to find the answer. Let AN represent the number of ways to make deposit for N dollars. Using only $1, $2, and $5 bills. Assume the order matters. Assume the order of making deposit matters. Assume the order of making deposit matters. So let's try to find the current relation. Let's try to find the current relation for A sub n. A represents the number of ways to make deposit for N dollars. So the first deposit may be either $1 bill, $2 bill, or $5 bill. So there are 3 cases. Case 1. The first deposit is a $1 bill, it's a dollar bill. If the first deposit is a dollar bill, then we need to make a deposit for N-1 dollars. Then we need to make deposit for N-1 more dollars. Then we need to make deposit for N-1 more dollars. The number of ways to make deposit for N-1 dollars using only $1, $2, and $5 bills is A sub N-1. The number of ways to make deposit for N-1 dollars using $1, $2, $5 bill is A sub N-1. That's case 1. Case 2. If the first deposit if the first deposit is a $2 bill. Case 2, if the first deposit is a $2 bill, then we need to make deposit for m minus 2 more dollars. Then we need to make deposit for m minus $2. The number of weeks to make deposit for m minus $2 using only $1, $2, and $5 bills. Is a sub m minus 2. That's the number of ways to make deposit in case 2. In case 3, if the first deposit is a $5 bill, if the first deposit is a $5 bill, then we need to make deposit for m minus 5 more dollars. The number of weeks. Let's continue, case 3, continue. The number of ways to make deposit for m minus $5 using only $1, $2, and $5 bills. Is a sub m minus 5. That's case 3. For the final answer, we add all 3 cases together. For the final answer, a sub n is a sub m minus 1 plus a sub m minus 2 plus a sub m minus 5. Add all 3 cases together. And since the index cannot be negative, this formula only works if n is greater or equal to 5. This formula only works if n is greater or equal to 5. Now, what if n is less than 5? What if n is less than 5? If you want to make deposit for less than $5, you cannot use your $5 bills. So you can only use your $1 and $2 bills. You cannot make deposit for $5 bills. So there's only 2 cases. You either make deposit for $1 bill or make deposit for the second for $2 bill. You can make deposit for $5 bill if you make deposit less than $5. If you want to make deposit which is less than $5, you cannot use $5 bills. You can only use either $1 bill or $2 bill. So in this case, it's either there's only two cases: a sub n minus 1 plus a sub n minus 2. And this formula only works when n is greater or equal to 2. This formula only works when n is greater or equal to 2. When n is less than 2, we treat this as a special case. When n is less than 2, we treat this as a special case. A sub 0. In how many ways can we make deposit for $0? The answer is one way. That means doing nothing. Doing nothing means one way. So the number of ways to make deposit for $0 is 1. This way, there's only one way to make deposit for $0, which means doing nothing. A sub 1. In how many ways can we make deposit for $1? There's only one way. You make deposit for dollar bill. There's only one way. You make deposit using dollar bill. So that's the recurrent relation. That's the recurrent relation. We can write it as a sub 0 equal to 1. A sub 1 equal to 1. A sub 1 is a piecewise function equal to a sub n minus 1 plus a sub n minus 2 plus a sub n minus 5 if n is greater or equal to 5, equal to n a sub n minus 1 plus a sub n minus 2. If n is greater or equal to 2 but less than 5. That's the recurrent relation. Now the question asks, in how many ways can we make deposit for $10? That means we're looking for a sub 10. We're looking for a sub 10. But this is a recurrent relation. Since we don't know the closed form, there's no shortcut. We must calculate one by one. A sub 0 is 1. A sub 1 is 1. A sub 2. 2 is 2 equal to here. 2 is between 2 and 4, including 2. We use the second equation here. So plotting 2 for n, we have a sub 1 plus a sub 0, which is 1 plus 1 equal to 2. A sub 3, 3 is between 2 and 5. I use the second equation. A sub 2 plus a sub 1. A sub 2 is 2. A sub 1 is 1, which is 3. A sub 4. 4 is between 2 and 5. We use the second equation. It's a sub 3 plus a sub 2. A sub 3 is 3. A sub 2 is 2. 3 plus 2 is 5. A sub 5 is 5 here is greater than or equal to 5. We use the first equation now. A sub 4 plus a sub 3 plus a sub 0. A sub 4 is 5. A sub 3 is 3. A sub 0 is 1, which is 9. A sub 6, we use the first equation. That's a sub 5 plus a sub 4 plus a sub 1. A sub 6, a sub 5 is 9. A sub 4 is 5. A sub 1 is 1. That's 15. Next, for a sub 7, we have used the first equation. We have a sub 6 plus a sub 5 plus a sub 2, which is 15 plus 9 plus 2. 15 plus 9 is 24. 24 plus 2 is 26. A sub 8 is a sub 7 plus a sub 6 plus a sub 3. A sub 7 is 26. A sub 6 is 15. A sub 3 is 3. That's 41 plus 3 is 44. A sub 9 is a sub a plus a sub 7 plus a sub 4 which is 44 plus 26 plus a sub 4 is 5. That's 70 plus 5 is 75. For a sub 10, we use a sub 9 plus a sub a plus a sub 5. A sub 9 is 75, a sub a is 44, a sub 5 is 9. 75 plus 44 is 119. 119 plus 9 is 128. So we have 128 ways to make deposit for $10. That's the answer. Number 8, part D. Suppose you have only $2 and $10 bills. In how many different ways can you make a deposit for $20? So for this problem, we'll use recurrent relations. Let AN represent the number of ways to make deposit for $n. Using only $2 and $10 bills. Now assume we want to make a deposit for $n. Assume we don't make deposit for $n. In how many ways it can be complete? So the first deposit could be either a $10 bill or $2 bill. Since we only have $2 and $10 bills, the first deposit could be either a $2 bill or $10 bill. So there are two cases. Case 1. If the first deposit is a $2 bill, then we need to make deposit for m minus 2 more dollars. We need to make deposit for m minus 2 more dollars. The number of ways to deposit m minus $2 the number of ways to make deposit for m minus $2 using only $2 and $10 bills is a sub m minus 2, because a sub n represents the number of ways to make deposit for $n using only $10 and $2 and $10 bills. That's case 1. If the first deposit is a $2 bill. Case 2, the first deposit could be a $10 bill. Case 2, the first deposit is a $10 bill. If the first deposit is a $10 bill, we need to make deposit for n minus 10 more dollars. The number of ways to make deposit for n minus $10 is a sub n minus 10. The number of ways to make deposit for n minus $10 using only $2 and $10 bills is a sub n minus 10. That's the only two possible cases. So the number of ways to make deposit for $10 for n dollars. So the number of ways to make deposit for n dollars the number of ways to make deposits for n dollars, an equal to there are two cases. an equal to a sub n minus 2 plus a sub n minus 10. There are two cases. And for this recurrent relation, the index cannot be negative. So this formula only works if n is greater or equal to 10. Since the index cannot be negative, this formula only works when n is greater or equal to 10. But what if n is less than 10? What if n is less than 10? If we make deposit for amount less than $10, we won't be able to use $10 bills, so we can only use $2 bills. When we make deposit for total amount of less than $10, we won't be able to use $10 bills. We are only allowed to use $2 bills. So if we only allowed to use $2 bills, we have a, there's only one case, a sub n minus 2. This formula only works for n greater or equal to 2 because the index cannot be negative. This formula only works when n is greater or equal to 2. Then for n less than 2, we have two special cases. When n is less than 2, we have two special cases. A sub 0. The number of ways to make deposit for $0 is 1. There's only one way to make deposit for $0, which means doing nothing. There's one way to make deposit for $0, which means doing nothing. In how many ways can we make deposit for $1? Since we don't have dollar bill, there's no way you can make deposit for $1. So we have 0 way to make deposit for $1. Next, we try to find out in how many ways we can make deposit for $20. If we want to make deposit for $20, we try to find a sub 20. We try to find a sub 20, but we don't know the closed form for this formula, so we must compute A0, A1, A2 up to A20. There's no shortcut. Since we don't have the closed form of the formula, we must compute one by one. Let me rerun the formula, put it here. A sub 0 is 1. A sub 1 is 0. A sub n equal to a sub n minus 2 plus a sub n minus 10 if n is less or equal to 10, is greater or equal to 10. A sub n equal to a sub n minus 2 if n is between 2 and 10. Now let's try to compute a sub 20. A sub 0 is 1, a sub 1 is 0. A sub 2 is less or equal to n. We use the second formula. If I plug in 2 here, 2 minus 0 is 2 minus 0. 2 minus 2 is a sub 0. 2 minus 2 is 0, so we get a sub 0. A sub 0 is 1. A sub 3 minus 1 is 3 minus 2 is 1. So I get a sub 1. A sub 1 is 0. A sub 4. 4 is less than 4 is between 2 and 10, so we use the second formula. That's a sub 2, which is 1. A sub 5 is a sub 3. A sub 3 is 0. A sub 6 is a sub 4. A sub 4 is 1. A sub 7 is a sub 5. A sub 4 is 0. A sub 8 is a sub 6. A sub 6 is 1. A sub 9 is a sub 7. And a sub 7 is 0. A sub 10 is a sub a. So a sub 10, we use the first formula. That's because n is greater or equal to 10, we use the first formula. That's a sub a plus a sub 0. A sub a is 1. A sub 0 is also 1, which is 2. A sub 11 is a sub 9 plus a sub 1. A sub 9 is 0. A sub 1 is 0. I get 0. A sub 12. A sub 12 is a sub 10 plus a sub 2. A sub 10 is 2. A sub 2 is 1. 2 plus 1 is 3. A sub 13 is a sub 11 plus a sub 3. 0 plus 0 is 0. A sub 14 is a sub 12 plus a sub 4. A sub 12 is 3. A sub 4 is 1. 3 plus 1 is 4. A sub 15 is a sub 13 plus a sub 5. A sub 13 is 0. A sub 5 is also 0. 0 plus 0 is 0. A sub 16 is a sub 14 plus a sub 6. A sub 14 is 4. A sub 6 is 1. 4 plus 1 is 5. A sub 17 is a sub 15 plus a sub 7. A sub 15 is 0. A sub 7 is also 0. 0 plus 0 is 0. A sub 18 is a sub 16 plus a sub a. A sub 16 is 5. A sub a is 1. 5 plus 1 is 6. A sub 19 is a sub 17 plus a sub 9. A sub 17 is 0. A sub 9 is 0. 0 plus 0 is 0. A sub 20 is a sub 18 plus a sub 10. A sub 18 is 6. A sub 10 is 2. 6 plus 2 is 8. So there are 8 ways to make deposit for $20. There are 8 ways to make deposit for $20 using only $2 and $10 bills. Number 9. Find a solution for each of the following equivalent relations. Part A. A(n) equal to 7 a sub n minus 1 minus 10 a sub n minus 2 for n greater or equal to 2. And we have two initial conditions, that a0 equal to 2, a1 equal to 1. Since every term contains a sequence a sub I, this is homogeneous equivalent relation. This is a homogeneous equivalent relation. Since every term contains ai, this is a homogeneous equivalent relation. So first of all, let an equal to x to the power n. Let a sub n equal to x to the power n. Then a sub n minus 1 is x raised to n minus 1. And a sub n minus 2 is x raised to the power of n minus 2. If I substitute, I have x to the power n equal to 7 times x raised to n minus 1 minus 10 times x raised to 10 minus 2, n minus 2. Then divide every term by the lowest power of x. Divide every term by the lowest power of x. If I divide every term by x raised to power of n minus 2, if I divide every term by x raised to n minus 2, this equation can be rewritten as s squared equal to 7x minus 10. Simplify, I can move everything to the left side. S squared minus 7x plus 10 equal to 0. This is called a characteristic equation. This is called a characteristic equation. Let's call a characteristic equation. And next, we solve the equation for x. Solve the equation for x. I can solve the equation by factoring. X minus 2, x minus 5, set equal to 0. I have s equal to 2, s equal to 5. So if I substitute 2 for x, I have 2 raised to power n. If I substitute 5 for x, I have 5 raised to power n. They are called linearly independent solutions. We call the first solution S1. We call the second solution S2. And how do we know the general solution? How do we know the general solution? For general solution, there's a rule. It says, if the current relation has degree 1, if the current relation has degree 1, then the general solution has the form of C1 times S1. If the current relation has degree 2, the general solution AN is in the form of C1 S1 plus C2 S2, where C1 and C2 are constants. S1 S2, they are linearly independent solutions. If the current relation has degree 3, then the general solution is AN equal to C1 S1 plus C2 times S2 plus C3 times S3 and so on. Now how do we find the degree? Degree is the difference between the highest and the lowest index. Degree is the degree of the current relation is the difference between the highest index and the lowest index. Here the difference between highest and lowest index is 2. So this recurrent relation has degree 2. This recurrent relation has degree 2. So the general solution must be in this form. C1 S1 plus C2 S2, where C1 C2 are constants. S1 S2, they are independent solutions. So since this recurrent relation has degree 2, the general solution has the form of AN equal to C1 times S1 plus C2 times S2, where C1 C2 are constants. S1 is 2 raised to power n. S2 is 5 raised to power n. Next, we need to solve for C1, C2 based on the initial condition. Next, we need to solve for C1, C2 based on the initial condition. For A sub 0, if I plug in 0, if I plug in 0 for n, I have C1 times 1. 2 to the power 0 is 1. 5 to the power 0 is also 1. If I plug in 0 for each n, I must get 2 here. So first equation equal to 2. If I substitute 1 for n, 2 raised to power 1 is 2. 5 raised to power 1 is 5. If I substitute 1 for each n, I get 1. Then we have two equations here. First equation, C1 plus C2 equal to 2. Second equation, 2c1 plus 5c2 equal to 1. If I multiply first equation by negative 2, I have negative 2c1 minus 2c2 equal to negative 4. If I multiply first equation by negative 2, I have negative 2c1 minus 2c2 equal to negative 4. And leave the second equation the same. What do we have? I have 2c1 plus 5c2 equal to 1. If I add the equation together, I have 3c2 equal to negative 3. If I divide both sides by 3, c2 equal to negative 1. Then I plug in negative 1 for c2. If I substitute negative 1 for c2, I have c1 plus negative 1 equal to 2. Add 1 to both sides, c1 equal to 3. So I have c1 equal to 3, c2 equal to negative 1. So for the solution, so for the final solution, we substitute c1, c2 into the general solution. I have an equal to 3 times 2 to the power n minus 1 times 5 to the power n. That's the solution to this recurrent relation. Number 9, part B. A sub n equal to negative 6 a sub m minus 1 minus 9 times a sub m minus 2 for n greater than or equal to 2. Initial condition is a sub 0 equal to 3, a sub 1 equal to negative 3. Since every term in the equation, contains the sequence a sub I, this is a homogeneous recurrent relation. Since every term contains the sequence a sub I, this is a homogeneous recurrent relation. And also, since the difference between the highest and the lowest index is 2, this homogeneous recurrent relation has degree 2. Next, let's solve this recurrent relation. Find the characteristic equation first. Let a sub n equal to x raised to power n. Then a sub n minus 1 can be rewritten as x raised to n minus 1, and a sub n minus 2 equal to x raised to power of n minus 2. If I substitute each ai, I have x raised to power n equal to negative 6 x raised to power of n minus 1 minus 9 raised to the power of n minus 2. Divide every term by the lowest power of x. I have lowest power of x is x raised to the power of n minus 2. If I divide every term by s to the power of n minus 2, I have x squared equal to negative 6x minus 9. Then move everything to one side. I have x squared plus 6x plus 9 equal to 0. This is the characteristic equation. This is the characteristic equations. Then solve the equation for x. This equation can be factored as x plus 3 times x plus 3 equal to 0. That means x plus 3 is 0. X plus 3 squared equal to 0. If I solve the equation, x equal to negative 3. And since this term x plus 3 has power 2, we say this solution has multiplicity of 2. What does multiplicity means? Keep this idea in mind. If the characteristic equation contains x minus r to the power 2 equal to 0, then the solution s equal to r has multiplicity of 2. If the characteristic equation contains x minus r to the power of 3 equal to 0, then the solution s equal to r has multiplicity of 4, multiplicity of 3. If the characteristic equation contains x minus r raised to power 4 equal to 0, then the solution s equal to r has multiplicity of 4. If this term doesn't have any power, if there's no power here, then the solution s equal to r has multiplicity of 1. If there's no power here, then the solution s minus r has multiplicity of 1. So in this case, we have x plus 3 to the power 2 equal to 0. If I solve the equation s equal to negative 3, this solution has multiplicity of 2. So if I substitute negative 3 for x, I have negative 3 raised to power n. This is called the independent solution. If I substitute negative 3 for x, I have negative 3 raised to power n. This is called the linearly independent solution. The general solution. What's the general solution here? Be very careful. What's the general solution? This homogeneous nuclear relation has degree 2 because the difference between the highest and the lowest index is 2. This homogeneous nuclear relation has degree 2. So the general solution must have the form of an equal to C1 times S1 plus C2 times S2. Since this homogeneous nuclear relation has degree 2, the general solution must have the form of C1 times S1 plus C2 times S2. But here we only have one independent solution. What can we do for the other? How can we find the other linear independent solution here? We only have one linear independent solution. How can we find the other one? There's a rule here. Be very, very careful. If a solution has multiplicity of 2, if a solution has a multiplicity of 2, the independent solutions, the linearly independent solutions, are r raised to power n and n times r raised to power n. If the solution has multiplicity of 2, the linear independent solutions are r raised to power n and n times r raised to power n. And same thing. Similarly, if the characteristic equation contains x minus r to the power 3. The solution has multiplicity of 3. The linearly independent solutions are let me say it this way. And r raised to power n and n times r raised to power n are linearly independent solutions. That's better. They are linearly independent solutions. If a solution has multiplicity of 3, then r raised to power n, n times r raised to power n, and n squared times r to the power n, they are linearly independent solutions. They are linearly independent solutions. And here, if a solution has multiplicity of 4, then r to the power n, n times r to the power n, n squared times r to the power n, and n to the power 3 times r to the power n, they are linearly independent solutions. So keep this rule in mind. And same rule works for higher multiplicity. It works for multiplicity of 5, 6, 7, 8, 9. Same rule works for higher multiplicities. So here, this solution s equal to negative 3 has multiplicity of 2. So x raised to power n, negative 3 raised to power n, and n times negative 3 raised to power n. They are independent solutions. They are linearly independent solutions. So if I substitute, I have an equal to c1 times negative 3 raised to power n plus c2 times n times negative 3 raised to power n. That's the general solution. Next, we need to solve for c1, c2 based on the initial condition. For a sub 0, we plug in 0 for each n, and the equation equal to 3. For a sub 0, we plug in 0 for each n, and the equation equal to 3. If I substitute 0 for n, I have c1 times 1. If I substitute 0, I get 0 here, and that equal to 3. For a sub 1, I substitute 1 for each n, then the equation equal to negative 3. I substitute 1 for each n. Negative 3 raised to power 1 is negative 3. n by itself is 1. Negative 3 raised to power 1 is negative 3. And this equation equal to negative 3. If I solve for the first equation, I have c1 equal to 3. If I solve for the first equation, I have c1 equal to 3. If I simplify the second equation, I have negative 3 c1 minus negative 3 c2 equal to negative 3. If I substitute 3 for c1, I have negative 9 minus 3 c2 equal to negative 3. Add 9 to both sides. Negative 3 c2 equal to 6. Divide both sides by negative 3. c2 equal to negative 2. So we have solution c1 equals to 3, c2 equal to negative 2. I can substitute here. substitute 3 for C1, substitute negative 2 for C2. I have an equal to 3 times negative 3 to the power n plus minus 2 times n times negative 3 to the power n. That's the solution to this homogeneous nuclear relation. That's the solution to this homogeneous nuclear relation. Number 9, part C. An equal to 2a sub n minus 1 plus 2 to the power of n squared for n greater or equal to 2. A sub 1 equal to 4. So in this equation here, this term doesn't have a sequence of ai. This term doesn't have a sequence a sub I. So this is not this is a non-homogeneous nuclear relation. This is a non-homogeneous nuclear relation. This part is called a non-recursive part. This part is called a non-recursive part. And this part is called the associated homogeneous nuclear relation. This part is called associated homogeneous nuclear relation. For a non-homogeneous nuclear relation, we first of all solve for associated homogeneous nuclear relation first. The general solution is called the homogeneous solution. Solve an associated homogeneous nuclear relation first. The solution is called the homogeneous solution. So I first of all solve the associated homogeneous nuclear relation first. A sub n equal to 2 times a sub n minus 1. This nuclear relation has degree 1 because the difference between the highest and the lowest index is 1. This nuclear relation has degree 1. Let a sub n equal to x raised to power n. Then a sub n minus 1 is x raised to the power of n minus 1. If I substitute, I have x raised to power n equal to 2 times x raised to the power of n minus 1. Then I can divide both sides by the lowest power of x. Divide both sides by the lowest power of x. I get s equal to 2. This is the characteristic equation, and it's also the solution of the characteristic. It's also the solution of the characteristic equation. This is the characteristic equation, and it's also the solution. The linearly independent solution when we substitute 2 for x, I have a linearly independent solution s1 equal to 2 raised to power n. So since this nuclear relation has degree 1, the general solution to the homogeneous nuclear relation is C1 times S1, which is C1 times 2 to the power n. That's the general solution to the associated homogeneous nuclear relation, which is also called homogeneous solution to this nuclear relation. So that's A sub n, AH of n. That's the homogeneous solution. This H here stands for homogeneous solution, equal to C1 times 2 to the power n. This is called the homogeneous solution to this nuclear relation. Next, we need to find the particular solution. For the general solution for any non-homogeneous nuclear relation has two parts: homogeneous solution and particular solution. Adding up, we get a general solution to this non-homogeneous Lagrange relation. Homogeneous solution plus particular solution is the general solution to this non-homogeneous Lagrange relation. So next, let's try to find particular solution. Let's try to find a particular solution. Look at the non-recursive part. Look at the non-recursive part. This is a polynomial of degree 2. This is a degree 2 polynomial. Here is the rule. If the non-recursive part is a polynomial of degree k, then the particular solution must be a general polynomial of degree 2. And the non-recursive part here is a polynomial of degree 2. The non-recursive part is a polynomial of degree 2. So the particular solution must be a general second degree polynomial, which is an squared plus bn plus c. Since the particular solution also satisfies this Lagrange relation, we can plug in this particular solution to solve for a, b, and c. We can plug in this particular solution into this Lagrange relation, solve for a, b, and c. So in order to plug in, let's find a sub n minus 1 first. For a sub n minus 1, I replace each n with n minus 1. I have a times n minus 1 squared plus b times n minus 1 plus c. Then we plug in a sub n and a sub n minus 1 into this Lagrange relation and try to solve for a, b, and c. If I plug in a sub n is an squared plus bn plus c. On the other side, we have 2 times 2a sub n minus 1. 2 times a sub n minus 1. So number 2 stays the same. A sub n minus 1 is a times n minus 1 squared plus b times n minus 1 plus c plus 2n squared. Substitute. Replace a sub n with a squared plus an squared plus bn plus c. Replace a sub n minus 1 with a times n minus 1 squared plus b times n minus 1 plus c. Then try to match the coefficient, solve for a, b, and c. Let's simplify the right side first. On the right side, if I distribute 2, I have 2a times n minus 1 squared plus 2b times n minus 1 plus 2c plus 2n squared. If I expand the perfect square, I have 2a times n squared minus 2n plus 1 plus 2b times n minus 1 plus 2c plus 2n squared. Distribute 2a, we have 2a n squared minus 4an plus 2a. Distribute 2b, we have 2bn minus 2b plus 2c plus 2n squared. Then try to combine like terms. Put n squared together, we have 2a plus 2 times n squared. Then put the term of n together. We have negative 4a plus 2b times n. Then put all constant terms together, plus 2a minus 2b plus 2c. Bring the left side down. We have an squared plus bn plus c. Next, let's try to match the coefficient. Coefficient of n squared is a equal to 2a plus 2. If I solve an equation for a, I have negative a equal to 2, so a equal to negative 2. Next, we have b equal to negative 4a plus 2b. Subtract 2b from both sides. Negative b equal to negative 4a. A is negative 2. So negative b is number a. B equal to negative a. Next, we can try to solve for c. Match the constant. C equal to 2a minus 2b plus 2c. Then subtract 2c from both sides. Negative c equal to 2a minus 2b. A is negative 2. B is negative a. So if negative c equal to negative 4 plus 16, that's 12. So c equal to 12. C equal to negative 12. That's a, b, and c. So once I know a, b, c, I can plug in a, b, c into the particular solution. So the particular solution is negative 2n squared minus an minus 12. That's the particular solution. And the general solution, a sub n, the general solution a sub n is the homogeneous solution plus particular solution. The general solution is homogeneous solution plus particular solution. And we know that the homogeneous solution is C times C1 times 2 to the power of n. C1 times 2 to the power of n. Particular solution is negative 2n squared minus an minus 12. Next, I can use the initial condition. To solve for C1. Initial condition says A1 equal to 4. Initial condition says A1 equal to 4. Which means if I substitute 1 for each n, this equation must equal to 4. So if I substitute 1 for n, 2 to the power 1 is 2. I get 2C1. If I substitute 1 here, I have negative 2, negative a, negative 12. That equal to 4. Then solve the equation for C. I have negative 10 minus 12 is negative 22. Add 22 to both sides, I get 26. So C1 equal to 13. Once I know C1, I can plug in C1 here to find an. So a sub n equal to 13 times 2 to the power n minus 2n squared minus an minus 12. That's the solution. That's the solution to this current relation. That's the solution to this current relation. Number 9, part D. An is negative 5 a sub m minus 1 minus 6 a sub m minus 2 plus 42 times 4 to the power n for n greater or equal to 3. We have two initial conditions here. So since this term doesn't contain the sequence a sub I, this term doesn't contain the sequence a sub I, this is a non-homogeneous current relation. This is a non-homogeneous current relation. This is the non-recursive part. This is the non-recursive part. And this part is the associated homogeneous current relation. This part is the associated. This is an associated homogeneous current relation. This is an associated homogeneous current relation. Let's first of all find a homogeneous solution. First. Homogeneous solution is the general solution of an associated homogeneous current relation. The homogeneous solution to this current relation is the general solution of this associated homogeneous current relation. So let's solve this associated homogeneous current relation first. A sub n is negative 5 times a sub n minus 1 minus 6 times a sub n minus 2. Let's solve this homogeneous current relation first. let a sub n equal to x to the power n, then a sub n minus 1 is x raised to the power of n minus 1, and a sub n minus 2 is x to the power of n minus 2. Then plugging, we have x to the power n equal to negative 5 times x to the power of n minus 1 minus 6 times x to the power of n minus 2. Then divide every term by the lowest power of x. Divide every term by the lowest power of x. Lowest power is x raised to n minus 2. If I divide, I have x squared equal to negative 5x minus 6. Then move everything over. We have x squared plus 5x plus 6. x squared plus 5x plus 6 equal to 0. This is the characteristic equation. This is a characteristic equation. This is a characteristic equation. Next, let's solve the equation for x. I can factor this as x plus 2 times x plus 3. If I set equal to 0, I have s equal to negative 2 and s equal to negative 3. Here we have two solutions. Next, I substitute this 2x here. Substitute x. I get two independent solutions. Negative 2 to the power n. That's the first one. The second one is s2 equal to negative 3 to the power n. Those are the linearly independent solutions. Those are the linearly independent solutions. Those are the linearly independent solutions. Since this Newtonian relation has degree 2, because the highest index and the lowest index, when we subtract, the difference is 2. So since this Newtonian relation has degree 2, the general solution is in the form of C1 times S1 plus C2 times S2. And the general solution to this associated homogeneous Newtonian relation is the homogeneous solution. The general solution to this homogeneous Newtonian relation is the homogeneous solution AH of n that equal to C1 times S1 plus C2 times S2. That's the homogeneous solution, which is the general solution to this associated homogeneous Newtonian relation. That's called a homogeneous solution to this original Newtonian relation. That's called a homogeneous solution to this original non-homogeneous Newtonian relation. This is the homogeneous solution to this original Newtonian relation. Next, we try to find a particular solution. This particular solution, the non-recursive part, here the non-recursive part is in the form of a polynomial times r to the power n. Here the non-recursive part is in the form of a polynomial times r to the power n. And 42, a constant, is considered a 0 degree polynomial. A constant is considered the 0 degree polynomial. So here the non-recursive part is in the form of polynomial times r to the power n. Polynomial times r to the power n. And this r here, r is 4. This 4 is not one of the solution of the characteristic equation. This 4 is not one of the solution to this characteristic equation. So that's case 2. The particular solution must be in the form of general polynomial of degree 0 times r to the power n. So the particular solution must be in the form of general polynomial of degree 0. Here, this is a polynomial of degree 0. So the particular solution must be general polynomial of degree 0 times r to the power n. So the particular solution it must be in the form of a general 0-degree polynomial that's a constant. A general 0-degree polynomial is a constant times 4 to the power n. That's a particular solution. Now, just in case, if this number 4 is a solution of this characteristic equation, if this number 4 is a solution of this characteristic equation, there's an actual factor here. There's an actual factor. Everything looks the same. For particular solution, everything looks the same, but there's an actual factor here. Times n to the power m. M is the multiplicity of the root. M is the multiplicity of the root. So if 4 is a solution to the characteristic equation, then there's an actual factor here. In this problem, since number 4 is not a solution to the characteristic equation, so we don't have n to the power m here. We don't have this factor. That's the form of a particular solution. General polynomial of degree 0 times r to the power n, because 42 is a polynomial of degree 0. If this is a polynomial of degree k, then particular solution must be general polynomial of degree k times this 4 to the power n. So that's the particular solution. Since the particular solution also satisfies this recurrent relation, I can plug in and solve for A. Since this particular solution also satisfies this recurrent relation, I can plug in this particular solution and solve for letter A. So in order to plug in, let's compute A sub n minus 1 and A sub n minus 2. For A sub n minus 1, I plug in n minus 1 for n. For A sub n minus 2, I plug in n minus 2 for n. Next, let's plug in. Left side is A sub n, which is A times 4 to the power n. That's left side. Right side, we have negative 5 times A times 4 to the power of n minus 1 minus 6 times A times 4 to the power of n minus 2 plus the last term 42 times 4 to the power n. Let's first of all divide every term by the lowest power of 4. Here every term has a 4 raised to some power. Divide every term to the lowest power of 4. Lowest power of 4 is 4 to the power of n minus 2. So if I divide, I have A times 4 squared equal to negative 5 times A times 4 minus 6 times A plus 42 times 4 to the power 2. If I simplify, I have 16A equal to negative 20A, negative 6A plus 42 times 16. Combine like term here, combine like terms here. Negative 20 minus 6 is negative 26A plus 42 times 16. Then add 26A to both sides. I have 42A equal to 42 times 16. If I divide both sides by 42, letter A is 16. If I divide both sides by 42, letter A is 16. Once I know letter A, I can plug in A here. That's the particular solution. So the particular solution is 16 times 4 to the power n. The particular solution is 16 times 4 to the power n. That's the particular solution. The general solution is homogeneous solution plus particular solution. Homogeneous solution plus particular solution. homogeneous solution is C1 times negative 2 to the power n plus C2 times negative 3 to the power n. That's homogeneous solution. Plus particular solution, 16 times 4 to the power n. That's a particular solution. That's homogeneous solution. Yes, homogeneous solution. That's particular solution. Next, we try to use the initial condition. We try to use the initial condition here to find C1 and C2. So let me copy the initial condition here. A sub 1 is 56. A sub 2 is 278. A sub 1 is 56. A sub 2 is 278. Let me use the initial condition to find C1 and C2. A sub 1 is 56, means if I plug in 1, for n, this equation equal to 56. Negative 2 to the power 1 is negative 2. If I substitute 1 here, negative 3 to the power 1 is negative 3. If I substitute 1 here, 16 times 4 is 64. And this equation equal to 56. If I simplify this equation, it can be rewritten as negative 2c1 minus 3c2 equal to negative a. Second equation, second condition, if I substitute 2 for n, this equation will equal to 278. So for a sub 2, if I substitute 2 for n, I have c1 times negative 2 squared is 4. If I substitute 2 for n, negative 3 squared is 9. If I substitute 2 for n, 4 squared is 16. 16 times 16 is 256. And this equation equal to 278. If I simplify, it can be rewritten as 4c2 plus, 4c1 plus 9c2 equal to 22. Then we can solve these two equations for C1, C2. We can solve these two equations for C1, C2. If I multiply first equation by 2, I have negative 4c1 minus 6c2 equal to negative 16. And I leave the second equation the same. Then if I add an equation, I have 3c2, c1 can cancel, 3c2 equal to 6. Divide both sides by 3, c2 equal to 2. Once I know c2, I can substitute c2 here, solve for c1. So 4c1 plus 9 times 2 equal to 22. 4 times c1 plus 18. Subtract 18 from both sides. 4 times c1 equal to 4. c1 equal to 1. So here I know c1, c2. Substitute c1, c2 here. We find a solution to the Maclaurin relation. If we substitute c1, c2, we have a sub n equal to 1 times negative 2 to the power n plus 2 times negative 3 to the power n plus 16 times 4 to the power n. That's the general solution. Sorry, that's the solution. No, not the general. This is general solution. This is a solution to the non-homogeneous Maclaurin relation. This is a solution to the non-homogeneous Maclaurin relation. This is general solution. This is general solution, and this is a solution to the non-homogeneous Maclaurin relation.